Okay, my I was trying to. I haven't decided.
What else are you running for?
I haven't decided yet. There's so much available.
Good morning, everyone. Hi, everyone. It's really great to see you all here. Good morning, and I think we can. Is it too dark for you all?
No.
No? Okay. All right, don't sleep. Welcome to the Modernize Your Water Delivery System using SCADA for data collection, management, and efficiency. And for those of you who don't know me, I'm Raquel Flinker. I'm an engineer with the Colorado River District. I've been with the district for almost 1 year, which is kind of crazy to think. And one of my tasks is the point person here in the Gunnison River Basin. So if you need help with anything, hopefully I can assist. So a few housekeeping notes, and this is mainly for people who are joining us virtually. We have over 20 people virtually. So the first is that we ask that everyone keep their microphones off, and as well as the cameras, because sometimes there's a bandwidth issue. And then second is that after every panelist, we'll have a Q&A session. We hope to have some questions from our audience here, and we'll also try to have some questions from our virtual audience. So if you have questions, there is a Q&A button in your Zoom screen, and you can put your questions in, and we'll try to have those asked and hopefully answered. And so before we get into the workshop, I would briefly like to talk about the Colorado River District. So the map on the left has the district. We are composed of 15 counties here in the Western Slope. And we were created in 1937 to lead in the protection, conservation, use, and development of water resources of the Colorado River Basin. And we were also created to help the state protect Colorado's entitlement in the Colorado River Compact. And so, maybe I should take this with me. Just wanted to show this map. This is a map of temperature increases from 1895 to 2018. And as you can see, counties such as Moffett, Mesa, Ouray have had an increase in temperatures of over 4 degrees Fahrenheit. And with a warming and drying climate that we're seeing and experiencing, there's research that shows that for every 1 degree Fahrenheit rise in temperature, stream flow is reduced between 3 to 5.2%. And so the workshop today, we hope will address how can we make our water systems more efficient and more resilient in the future if we're looking at less water potentially available for us. So how can we ensure that our water delivery systems have water into the future? And here's the agenda for today. And I would like to introduce and thank Susie Bilberry with the Delta Conservation District. She She has really. Yeah, you are talking. She has really been amazing. It has been amazing to work with her organizing this workshop. So thank you, Susie. And we do have several presentations today, as you can see, and we really hope that you enjoy it. And to get us started, I would like to invite Paul Maudlin. He will present or introduce our first speaker.
So I'm Paul Maudlin, and I'm from the Delta Conservation District, and there's a few other supervisors here, I think. Dave Whittlesby, Dave, raise your hand, and Paul K. Meyer, everybody knows him. And Stephen, you'll have to supply your last name too. Morris. Morris, that's right. Okay. And anybody else? Okay. All right. So here's a slide. So I'm pleased to introduce Craig Ullman today.
Sorry, 1 second. Let me just share the screen here so that people who are virtual can also see it. There you go.
So do they know my name on the other end?
No, no, you can repeat it, please.
So Susie, I think you're supposed to be talking right now.
Oh, yeah.
So Craig is a professional engineer. He's a so-called water resource engineer with the Applegate Group. He grew up in Fort Collins, Colorado, went to high school, went to college. He's got a master's degree in civil engineering from CSU in 2000. He's currently president of the Applegate Group. Several locations, Hotchkiss, Glenwood Springs, and on the Front Range in Denver somewhere. So Applegate is a professional engineering firm that assists private, public, municipal entities in development of water resource from initial concept to project completion. Craig actually works and lives in Hotchkiss, so he's close by. During his career, Craig has worked on a wide variety of water infrastructure projects, including dam design, hydrologic and hydraulic analyses, dam breach analysis, and a variety of dam rehab projects. I first met Craig in like 2010 or 2011, associated with the Minnesota Canal when they were piping their open ditch as part of their salinity projects. And when they were doing the piping across the northern side of my orchard, I met Craig a couple of times, and I think I met the other local engineer that was kind of on site. I think his name was Teddy Martinez. Does that sound right? Yeah. So where's Teddy now? Has he moved on somewhere?
He's not with Applegate anymore. He moved back east for several years, and now he's actually back out west though in Mesa County. He's working for the county down in Junction. So.
Okay, good. Maybe I'll see him again then. And so at the bottom of the slide is just a couple of tools of the trade as far as Craig is concerned. On the right is some 24-inch HDPE pipe to move water, and on the left is a pressure reducing valve, a clay valve that is probably an application for some SCADA control. So with that, Craig.
So a couple disclaimers too is as I'm an engineer, it means I'm probably not the best about talking to groups of people, but I'll do what I can. Also, as Paul mentioned, Applegate Group we're an engineering design firm. We are not SCADA, a final like SCADA implementation firm. We've helped some of our clients through a lot of our ditch and reservoir projects kind of identify areas where SCADA could help them possibly improve their systems. And then usually we'll hand them off to someone else who can help them with the nuts and bolts of exactly which equipment to put in, who's going to maintain it, and all those things. So I'm supposed to just give a brief overview. Some of you in the room may know a lot of the stuff I'm already talking about, but just give a brief overview of what it is, maybe what it can do for systems, what it's done for some of the systems around here. Obviously, there's going to be some guys talking later about specifics that on projects that they've done, but so I guess here goes. Okay. So what SCADA is, I mean, it's an acronym, and there's about 20 different acronyms if you really dig into SCADA, but SCADA itself stands for Supervisory Control and Data Acquisition. So there's several components to a true SCADA system. Some of the things I'm going to talk about probably wouldn't classify as a true SCADA system, but I'll go over that later. But usually it's a system where you're taking technology and you're using it to monitor systems, acquire data from systems, and control them, usually from a remote location. Potential benefits, there could be a lot. Water conservation is one of the big ones. A lot of people have looked to implementing things like this because they can figure out ways of saving water. One of the ways that can happen is, I mean, if you have a reservoir, you can better time your reservoir releases. You can better manage your reservoir releases. As you know, you open your valve X inches, as the reservoir drops, the flow rate starts to drop. So you got to send someone back out there and adjust the valve again to try to keep your flow rates constant. SCADA can be used to kind of even that out and provide you a more even release. On your canal side, it can do the same thing. You're diverting off of a creek. You can, a lot of the creeks around here, as you guys know, they have a big diurnal. They're high one time during the day and they crash during another time. You get a cold snap and the creek crashes again, and you're constantly trying to go up to a head gate and to maintain the proper flow in your ditch. SCADA can help address that kind of a thing with the canal. Other canals, like you get down into the Grand Junction area, some of the big canals down there, they don't necessarily need to run based on demand at the same flow rate all the time, but they need a certain level in the canal to service all their lateral turnouts. And so it becomes challenging for them to maintain their canal levels at a variable flow rates. And so SCADA has been implemented in some instances down there with check structures to maintain canal levels at a static level despite changes in the flow rate in the canal. And then that provides a good level of service to all of their turnouts in the system. Other places it's been used as warning systems. This is an example that I think Steve Fletcher with Fire Mountain will talk about a little bit later, but this is a trash screen that's on the inlet to a siphon that passes under Little Creek and over to their main service area on Rogers Mesa. It's kind of a remote site. No one lives nearby. No one looks at it regularly. So there is some SCADA tied to that so that they can basically monitor how the screen is performing, and it can send alarms if the screen starts to plug to the ditch rider, who can then go out and check it. That way he's not having to go out there unless maybe there is an issue. It also helps them monitor here. It's a spillway that if this plugs, it spills down to the creek, and it's at least a safe place to spill, but obviously you don't want to be wasting water, especially if you've released it from your reservoir. So it'll send them a warning if they start to spill water down to the creek based on just monitoring the levels. So actually, increased delivery precision is another benefit. Obviously, if you're implementing better flow measuring devices and monitoring them remotely or collecting better data on a regular basis, you're going to be able to increase the precision of water you're delivering to the users. Decreased travel time in Western Colorado and even in Eastern Colorado. Some of the systems are pretty spread out. I mean, Fire Mountain's a good example over here where their head gate up on the reservoir, it takes half hour, 45 minutes to get up there and then back. And so if you're up there trying to change flows 3 times a day or monitor things, it's a lot of time on the road. So if you can kind of get some controls in there that allow you to change things without having to visit the site all the time, you can save a lot of travel time. You can also be in more than one place at once, essentially. If you want to change 2 things at the same time and they're a half hour apart, if you've got both of them with a full SCADA system, you can do that. And then just improved data collection. Data collection is, I think, a lot of times overlooked, but when we get involved with design on it, like on the engineering side of a project, so a lot of times all we got is the data that the state has. And depending on where you are in the state, in the Gunnison Basin, you go up in the upper Gunnison, the water commissioners are taking readings on the flumes once a month. And so that's what we have, is once a month we have a data point, past in the history. We don't really know how it's changing daily. We don't really know how the flows are changing like weekly. And 2, a lot of the flumes are just not in the greatest of shape. So a little history of SCADA. We obviously a long time ago identified the need. I mean, we used to have just a lot of people to run these more complex systems. And as population has increased, systems have expanded, the complexity has increased. There's a lot of industries that have been using SCADA pretty much since computers came out. And those have been some of the ones listed here. Water, wastewater treatment systems, very complex, continuously getting more complex with the additional regulations that are imposed upon them. Oil and gas industry, very distributed networks. They have to monitor a lot of sites at once, spread out all over the place. And rather than visiting those sites a lot, I mean, you guys have probably driven I-70 through Rifle and you see all the antennas and solar panels, and they're monitoring a lot of that stuff remotely because it's tough to get to all of those sites. Electric power generation and transmission. I mean, you're talking about a nationwide grid now. I mean, to monitor that there's a benefit to having a central control station that can kind of see what's going on at one time. Manufacturing doesn't apply to you guys, but it's another place that SCADA is commonly used. I actually, as a side note, my wife runs an herbal tea company up in Hotchkiss on our property. We have a little machine that packages the tea, and there's all sorts of little sensors, and there's a computer in there that's watching the sensors, and it tells us if there's something wrong. It tells us if we're out of some materials. And so there's all these different little things happening that's being monitored. So it's almost like a little SCADA system in that one machine. And I mean, that's pretty common with manufacturing. Go to bigger, obviously, like automobile manufacturing plants, and they have SCADA all over the place monitoring the systems as the cars go through. But transit systems is another. CDOT, has essentially a SCADA system with a lot of their information on their road conditions and their cameras and things. More recently, it has started to trickle down to irrigation systems. In the past, irrigation systems were pretty much open ditches. Guys went out, changed the gates, and that's how it was. But more and more people are recognizing how some of this could be used on the irrigation systems and the reservoir systems to improve the operations. I kind of broke this out on different levels of what I would call SCADA, but some of these probably wouldn't classify as a true SCADA system, but trying to just think it through and present it in a logical manner is kind of the lowest step is just local monitoring. This is where maybe you install a recording device on your head gate flume. That would probably be the most common one. Typically, head gate flumes are read by the water commissioner and recorded in the state system, however often they visit the site, and that's the data. Some sites we have just implemented basically a data logger and a level recorder there that monitors it, checks it every 15 minutes, records it to a data card. So that's a very basic level, obviously, but it does start to get you more data on your system and what's happening. Local monitoring and control is the next step, where you have a single site and you're going to install some monitoring and control devices. I'm going to go through all these in a little more detail, but another step up would be remote monitoring. Now you're able to access the site. You've basically cast the signal up to some form of communication. You're able to access it via cell phone or computer somewhere. But the next step after that is now you're not only monitoring it remotely, but you're controlling it. So now you can send signals back to the device and make adjustments to your system. And then a final step, which really isn't too common around here with the ditch and reservoir companies, is automated monitoring and control. And I'll talk about that a little bit. But so local monitoring, this is just a couple examples of things we've done. This is a site over on the east slope where they were trying to track augmentation return flows out of a ditch. It's just, there's a weir plate down in this structure, and then there's a data logger here. This is a Sutron device with just a simple float that goes in the stilling well, and then that's tracking their flows. So they go out and read that weekly and track their augmentation releases very accurately. This is a ditch over near Carbondale that we installed an influme on, and as part of that, we put a stilling well in, and there's another Sutron recording device in there. That then at the end of every year gives us very good accurate data on how their diversions changed daily and throughout the year. So they're very common to put on stream gauges, flumes, meters. Another common application is flow meters. If you have a pipe system, or there's other flow meters that can be implemented in open channels. Acoustic Doppler profilers are kind of one. Some of these, a lot of them would typically incorporate, if we're talking about local monitoring in this sense, I'm assuming that there's a data logger component in there. So you're gathering more than just a staff gauge and writing stuff down on a sheet of paper. And this is just an example of the recorder out of this flume here. And you can see how if the water commissioner was reading, here, and here, the state's curve would look dead straight on that. And if you really zoom in on this, you can start to see all the fluctuations, daily fluctuations. These usually were when the river crashed, you had a cold snap here. And, the ditch rider shows up here, and then resets the canal, and then it keeps getting cold, and so he resets the canal, and then it maintains for a while, but it really kind of gives us a lot better data, especially if we're looking at other improvements to the system. You know, what could you save? Like, what are your actual diversions every year, and what could you save possibly by implementing additional measures? The next step, as I mentioned, is when you start adding, in addition to local monitoring and control, you're adding some sort of control at the site. This is still, everything is contained at the site. There's no communication like remotely with anything, but this is an example of a structure we did, the Needle Rock ditch up on the Smith Fork of the Gunnison. And this was partially in conjunction with the ditch company through some funding with the RCPP project. What this is this is the stream here, and this is their head gate, and we've got a control box here. The signal from our measuring flume below this structure comes into here. There's basically a computer in there that's watching that, and you set the flow rate. We want 30 CFS. That's what we're in priority for. The gate will then open and close to maintain the flow rate, because the Smith Fork, especially in this spot, is extremely volatile. It varies. It can double in flow overnight very quickly. It can also crash overnight if it gets cold, because there's no reservoir storage or diversions above them. So they're pretty much a natural run stream right there. The kind of a downside to this is staff does have to visit the site to make changes. They can't change this site remotely. Someone has to physically go up there and type in the new flow rate. So a typical site would consist of a sensor or multiple sensors. This site, we did add some level sensors in there to also be tracking kind of the river level and the level in the, below this is a stilling pool here. And so we track the level of that just to see if there's anything going on, because there's a screen in between the flume and this point. So if the level hasn't changed, but the flume suddenly sees a decrease in flow, we know the screen is plugging. And so then that gets tracked. And ultimately, this is supposed to get put into a remote system so that then it could send an alarm, but they're not there yet. So kind of another step is remote monitoring. This is a structure we did over on the east slope of Colorado. This was for the city of Arvada. They had a measuring flume at this site. It got wiped out in the 2013 flood. They wanted to measure 1 to 900 CFS on the inflow to one of their large reservoirs. And so we designed a concrete flume for them. And then you can't really see it, but there's a stilling well with a data logger here. And then they had their own SCADA folks, because they have their own SCADA system, came in and then tied that into their SCADA network so that they can then see this and see what the inflows are. That's tracked elsewhere. So the data logger component is offsite, but they did the tie-in for that. So some other common uses, obviously flow rates. I mean, you guys have used the stream gauge network throughout the state. You know, you can go in and check stream flows all over the state, and there's some canals that are also within that system. Canals, diversions, reservoir inlets, outlet flumes. Sometimes you want to track your canal levels. You want to know if what is the elevation of the canal is maybe more critical to you at a certain point. Reservoir levels, like how much storage do you have left, tracking that. So those are all benefits of just doing basic monitoring. Next step is you're doing that remote monitoring, but you want to be able to make changes to the system based on what you see. So now you're adding usually some form of a gate actuator to either an existing gate, or you're installing some new gates with actuators built into them. Sometimes these are single sites, sometimes it's multiple sites. Again, common uses would be stream diversion gates, reservoir outlets, trash screens, or major bifurcations, like some of the canals in Junction have a split where it splits 50-50 on the canal, or 60-40, and monitoring some of these key points within the system and controlling them can really save a lot of time if you're out there frequently, multiple times a day, trying to make adjustments. The picture there was a structure we did. I tried to find a better one, but this is the best one I could find that shows the box. But this was a device that I'll mention later that's made by a company called Rubicon, and it's a flow meter and a gate all in one. And that was put on their head gate diversion to monitor basically their stream diversions. And then you go to the highest level of kind of what SCADA might look like, and where you have an automated control and monitoring system. This really is not used, as far as my knowledge, within much of the US. They're kind of going towards it, probably out in California, maybe the Pacific Northwest, where there's some very large irrigation systems out there that are really trying to hone in on their efficiencies. But where this picture is from is, it's one I kind of borrowed from Rubicon Systems. They're a gate manufacturer in Australia that was born out of in 2007 through 2010 or so. They had a very extreme drought. Stream flows were half what they were. Kind of sounds familiar, right? Where we're unfortunately at right now. But the government, they're very large systems, and the government came in, and Rubicon kind of was born out of this, and they put 20,000 of these gates in throughout the system. They gated everything. You went from wooden checkboards to all these gates. The gates talk to each other. They know if the farmer can go online, he orders 5 CFS water, I want it here at 6 a.m. All the gates communicate up clear to the river diversion. It has learned through past experience, the system has learned how long it takes that water to get there, what gates need to open and close at what times. I mean, you can imagine the extensive amount of infrastructure that is required and the investment that the Australians put into that system. But it increased their efficiency pretty substantially, and that's their breadbasket area. So so some of the components, I'm just touching this high level, but usually you have some form of sensors there, and I'll go into different sensors later. But some other terminology that you've probably heard: RTU, remote telemetry unit, or remote terminal unit. These are basically, if you have a site and you have multiple sensors that you're going to then cast to the satellite or some form of communication, you'll have an RTU the sensors will feed the data into the RTU, which will then transmit the data to another location. A lot of times, instead of an RTU, because RTUs and PLCs, programmable logic controllers, kind of have overlapping tasks sometimes, but PLCs are a little more flexible. They're used a lot in local control, like that needle rock head yet I showed you. There's a PLC there because it needs to be programmed, custom programmed to make decisions how to open and close the gate. And so that requires a PLC on site. If you're going to be making the decisions elsewhere, then you maybe don't need a PLC right at the site itself. HMI is another common acronym. It's a human machine interface. Basically, it's a screen. I mean, anymore they're going to mostly touch screens because they're very easy to access and navigate. But anything from just a little touch screen at the site, like we have at that needle rock, to maybe if you're casting everything back to a home base, you have a computer screen that you can access everything through. And I think one of the earlier photos I showed was a room, basically probably for, let's say, a large municipality like the city of Los Angeles and their water system. They'll have a whole room full of screens just monitoring their whole system. So other things that are typically included are, radio, some sort of communication, either a radio, cellular, satellite. It depends on your site, obviously. Actuators are just gate motor operators, and there's lots of different kinds of those out there. You got to have a power system. Most commonly with these distributed sites, it's going to be some form of solar PV with a battery system. There are a few sites, if you happen to have AC power and you want to pay for a meter, sometimes that makes sense. And then one overlooked thing is a grounding system, because obviously if you're putting a radio up there, you're creating a lightning rod essentially, and you got to protect that from hits. So a grounding system can become very key as well. This is another thing I just borrowed off the internet. This is, I tried to find, you Google like what a typical system map might be, and they're pretty crazy because they're not really geared towards what we're talking about with irrigation systems. But this was the most applicable one I found, where you have maybe some monitoring sensors and some actuators at a site that are fed into an RTU, which then communicates via some form back to a master unit, say at an office somewhere where you have a computer. You have maybe another site where you have kind of a similar setup, but you have a logic controller there that is making some of the decisions within itself, but then casting that data back to the base as well. We really don't get into this with the systems we're talking about, but so getting into sensors just a little bit, there's the most common one is some sort of water level sensor, because if we know water level, we can relate that usually with the flume, obviously, to flow rate. And also sometimes you are just interested in the water level because it may relate to us, are you spilling or not? So there's a lot of different kinds out there. There's floats. This is a Sutron device. These are very commonly used around the state because of their simplicity. It's basically down below here, there'll be a float on one end of a cable and a weight counterweight on the other, and that just rotates this shaft, which there's an encoder built in there that then knows how the water level is changing. And those usually, they have a data logger built into them, so you can plug a card in at the end of your season, let's say, and it automatically downloads the year's worth of data to there. There's the other ones, pressure transducers are another one that I'm labeling these as contact type. These have something that's actually touching the water. This is a pressure transducer, and I see someone brought some up here too. So these are actually immersed in the water. Another one that is frequently used on reservoirs is a bubbler system, where it's basically spitting out bubbles and measuring the pressure required to discharge a bubble from the end of a tube. And by knowing how much pressure it took to discharge the bubble, it knows basically what the pressure is sitting on the end of the tube. Non-contact sensors are getting more and more common. Ultrasonic sensors, basically, and radio frequency sensors, basically are a device that'll sit above the water surface looking down at it, but they don't ever touch the water. It's just basically measuring the distance from your device, be it one of those two, down to the water level. And then a third one would be what I guess I doubled up contact, but there are some older ones that are just contact sensors. They know if they're wet or not. That's it. And so they have been used before as a high low. If you're trying to maintain a canal level within a certain range, you could set, one sensor low, one sensor high, and it knows, okay, you're above the set point, you're below the set point, but it doesn't tell you the actual level. So those are probably used less and less as these other options become more available. Getting into like flow meters, velocity meters. Sorry. That's all right. There's a lot of different flow meters out there in the last 10 years. I mean, there's mechanical meters, which were more common a long time ago, just the old propeller style meters. A lot of people, I mean, these were used a lot out in the Pacific Northwest. I mean, their whole systems were using propeller meters to meter all the farmer turnouts, but they've slowly been converting to things like these. This is an electromagnetic meter made by Symmetrics. This is an ultrasonic meter made by Metafim. But they've been converting to those because of the maintenance on these. The bearings on those wear out eventually. Usually they're replacing bearings depending on how dirty your water is, possibly every 2 to 3 years. And that gets to be a problem if you have 1,000 of those across your system. So a lot of people are going to more of these. These also have data loggers that you can get as an option on them. Some of them even have them built in. Other options, this is a acoustic Doppler meter that can be mounted either inside a pipe or in a rectangular channel or even in an open channel if it's fairly prismatic, but it's basically tracking the velocity. It develops a average velocity for your cross section, and then it needs to have a area relation curve, because this little sensor here then is measuring the water depth. So it says, okay, I'm this deep, which means based on my curve, I have this much flow area multiplied by my average velocity, and it spits out a discharge. So those are pretty flexible. They don't require you to be in a pipe, but they can be used inside a pipe as well. Some other ones that I'm not very familiar with, but I've seen on the market lately is this guy here is a laser meter, and basically it's a non-contact. It sits above the canal, and it's profiling the velocity of the canal using the area then to multiply times the velocity to get a flow rate. Other sensors that are periodically used, gate position sensors are very common, especially, I mean, obviously if you have an actuator, you kind of want to know what the gate position is. Sometimes it's just, hey, is the gate open or closed? Or a lot of times it will be more tracking the actual position of the gate. Temperature sometimes is monitored, usually not from a canal's perspective, but a lot of the stream gauges around the state may monitor temperatures. If you have a reservoir and you're held to any type of temperatures on your releases, you may have to monitor that. Some of the stream sites around the state monitor conductivity, mainly trying to track salinity. And then sometimes I've also seen folks using just optical cameras so they can, for more security than anything, so they can kind of see what's going on at the site. Integrated gates. There's several companies out there that are now selling, and this is not a concise list. I actually realized I forgot one that I'll mention here, but Watch Technologies, if you go to any conferences, they usually tend to be there. They basically make their own custom slide gates and they'll attach actuators to them. They also sell smart gates. They'll add level sensors so that you can basically program, and the gate can be kind of a standalone unit that you can then program if you want to maintain upstream level, downstream level, or a flow rate through the gate. They can provide that type of device. They can also provide actuators and equipment to automate existing gates. If you have a slide gate on your system and you want to basically have the actuator on there, Watch Technologies is a group that's worked with folks on that. Rubicon Water is another one that we've worked with on various projects. This was done quite a few years ago on the Front Range, but it was a pretty unique project where Rubicon sells various gates now. At this point, they have some overflow gates, some sluice gates, but they're the guys out of Australia that came out of their drought. Their gates are touted as being very accurate for flow measuring and controlling. So it's one, you put the gate in and the gate's measuring the flow. You don't need a supplemental flume. It monitors upstream level, downstream level, and the gate position. And by doing that, it's able to calculate the flow, but you can use it to control a variety of things and you can program it. These gates that we put on this structure, it was a ditch structure feeding. This was actually a reservoir outlet. The reservoir was going to get converted to be used partially just for the ditch, but also the local municipality needed a place for some flood storage. And so the town came in, built this structure for the ditch company. The ditch company agreed to lower the operating surface of the reservoir 2 feet and give that 2 feet as buffer storage to the town. And in exchange, they got a structure here that then communicates to their office and they can control remotely. So it was kind of a good partnership there with the city of Windsor. But there was a very complicated protocol that then had to be programmed into those gates as far as monitoring floods. The gates open under certain circumstances, close under other circumstances. Additional considerations that you definitely want, if you're considering a SCADA system and you start talking to either an engineer or a SCADA installer, there's a lot more to it. You got to really look at the appropriate level of SCADA. It can be easy to get carried away and start looking and, oh, we'll automate all these sites. But usually for the canal systems around here, the Australian model just, I don't think is really all that applicable. And I don't see it happening on a lot of the systems around here. A lot of our ditch systems are very small. Water rights get extremely complicated on the smaller ditches because you're going in and out of priority all the time. And to try to automate such small systems, I think would be very expensive and challenging without a lot of benefit. But that doesn't mean there's not an appropriate level that would provide a significant amount of benefit for those systems. Power availability. I mean, usually these things are just done with solar. Trash screens, however, are one that if you're going to incorporate a trash screen that you really need to consider. You know, the one we did with Fire Mountain is one of the few solar powered trash screens I know of. Most of those, if you're going to look at a site and you're going to be putting trash screens and automated gates in, you're probably going to be bringing power in unless you use something similar to the one that we did on Fire Mountain. Communications, what are your options at the site? Cellular, radio, satellite. I mean, satellite's becoming more and more common, I think, but cellular in Western Colorado can be tough. There's a lot of sites and canyons that you just can't get a cell signal to. And so then you're looking at almost a combination where maybe you bounce your signal out to a place where you do have cell service via line of sight radios. Data hosting, who's going to host your data? Are you going to bring it just back to your office and have access just in your office? Or do you want your ditch riders to have access on their cell phones, in which case you're not only bringing the signals back to a central control center, but then you need that data needs to go up onto the web somewhere. Who's going to host that data? How much are they going to charge per year to do so? Security. I mean, obviously you don't want just anyone able to get, if you are going to be putting stuff on the web, you don't want it just anyone to be able to see it or especially make changes to the system. Security at the site itself. We put in some of those Rubicon gates over in Denver, just kind of in a rougher area of Denver on Clear Creek for Coors Brewing Company. And within a few weeks, someone went in there and smashed the tar out of the control panels and things. And so they ended up putting razor wire fence around the whole thing. So, I mean, there's web security, but there's also physical site security depending on where you are. Site obstructions, are there trees that are small now that are going to become an issue later? You're going to need to maintain those, especially when you're looking at your solar panels and your communication antennas. longevity of the system, what is the equipment, you know, there's obviously, it's just like anything, you can buy something really cheap and it'll get you by for 5 years, but you know, some of the more expensive equipment might last longer. Redundancy can be a huge one depending on what you're trying to do. If you have a really critical site and then you just have to think through what happens if my one sensor at this site goes down? Does the gate shut? Does what happens if that, okay, and if it's a catastrophic, you know, failure of the canal or something, consider some redundancy in the system where you have maybe 2 sensors doing the same thing, so that if one goes down, there's a backup there on site. Also having, if you implement a system-wide SCADA where you have multiple sites and you're using multiple level sensors, try to use the same equipment at all the sites so that you can have one extra part on hand. You know, one of the projects we're doing, it's not really a SCADA system, but for Fruitland Irrigation Company, they're putting in a bunch of flow meters as part of their ditch project. Try to use, I mean, some of the meters you buy a 4-inch meter, you buy a 6-inch meter, you buy an 8-inch meter. To have extras on hand, you gotta have one of each size. Some of the meters now are insertion style meters where the insertion meter might work for a 4 to 12-inch pipe. So you have to have less backup products stored, so to speak. And then operation and maintenance, that I would say is one of the biggest ones to consider, is who's going to maintain this? Because a lot of the ditch riders and board members don't have the technical knowledge to maintain, you know, when something goes wrong on the software side, you got to have someone with experience to go in there. So usually you want to hopefully use someone that's fairly local that can be identified as your go-to person to come out and do maintenance and troubleshoot when needed. I mean, this is the one issue, I mean, with Rubicon systems, I mean, and others, if your service guys are quite a ways away, it can be difficult to get them to come out to one remote site in Western Colorado. That's one issue we've seen with multiple companies, I would say. And so it's something to consider. It doesn't mean that you can't use the product, but you also want to, I guess, one other thing, ask if you're looking at some of these gate technologies, ask the person who's selling the equipment, can I have someone else maintain this locally? Or does it have to be your technician? Because there are some products out there where they will not let a third party come in and work on it. It has to be their technicians. That gets to be a problem when their technicians are a month out to come on a site visit, versus maybe there's a local guy he knows how to program things, but if they won't give him the passwords to get into the machine, can't do you much good. So all discussions that you have when you're considering certain equipment. Certain additional information that, I don't know if any of you guys have heard of the Irrigation Training and Research Center out at Cal Poly. They have a very good website. They've done a lot of really good research on all sorts of things related to irrigation and canals. They've got some papers, and I don't know, is this presentation going to be available to people? I don't have links in here, but if you just do a search for these papers, these are 3 pretty good, fairly recent papers that they published. They've done a lot of work looking at various irrigation systems throughout California, the Pacific Northwest. They even came out and looked at Fire Mountain Canal, I know, around here. But they published some papers on some very practical, like, looks at SCADA systems on irrigation systems. They also are a good source if you're considering various flow meters. They've done a lot of testing on flow meters. You can go to their website, see if they've tested the meter that maybe you're considering. They'll rate it for a certain % error based on their testing that they do at their lab, because they have a full testing lab out in California. So those are some very good papers that kind of dive into some of the real world applications of the SCADA and things to consider. SCADA consultants, this is not a concise list by any means. These are some of the people, though, that we've worked with that we'll pass people off to when they're ready to, okay, we think we want to control this at this site and this at this site and bring it here. We'll say, okay, now it's time to get one of these guys involved. I mean, some of you guys may know Brian Mitchum. He's out of Paonia with Mountain Peaks Controls. They do work, historically, they did a lot of work for water treatment, wastewater type stuff. They're a company out of Denver as well. And they're now kind of trickling over and helping, I know, Fire Mountain and some others install their systems. Another guy, JUB Engineers, some of you may know, out of Grand Junction, recently hired Bob Norman. Bob Norman used to be with the Bureau of Reclamation, and he was pretty good with a lot of SCADA stuff there on the Bureau side. So he's now working part-time, I believe, at JUB. hydrologic. Bruce Bacon is a guy that we've done a lot of work with over on the East Slope. He's working with a lot of ditch and reservoir companies over there on implementing SCADA systems for those guys. And then obviously there's others out there, but I think that is all I had. Do you guys have questions? Yeah, Paul.
So the PLCs that are used to interrogate sensors and make decisions, is there kind of a go-to PLC that's typically used, or is it all over the place?
Alan Bradley is known as one of the better ones that I've, from hearing from some of the guys that actually have to maintain them on a regular basis.
Yeah.
Alan Bradley always seems to come up as far as one of the most reliable.
Programmed with ladder logic, is that what they're doing?
I think, yeah. And that is definitely something you want to talk about if you're with the SCADA consultant. What are they used to maintaining?
Yeah.
I mean, because you want them to be comfortable and familiar with it. And what have they, had the best experience with? I know, but like I said, the Alan Bradley's come up probably more than anything else as far as I've seen, but they're also on the higher cost end. So you usually get what you pay for.
Right.
Yeah.
Initial cost just on an average system and then annual cost to operate it or monitor it roughly.
I may punt that one to the guys that have put systems in and been maintaining them that are, I think, going to be talking later. Maybe they can answer that. I know install costs, it's going to vary so much on what sensors you're putting at a site, like are you doing radios or not? So it's like per site cost. You're in the, I mean, flow meters themselves are going to be in the $1,000, $1,000 to $2,000 just for a pipe flow meter. You start adding in, PLCs and things, you can easily get up to 5,000 per site pretty quick. If you start adding an actuator in, the actuator cost is going to be driven by what is your gate size, and they're not cheap, especially if you buy a high quality actuator. Rotork is one of the most common actuators we see implemented around. They're very good, but they're not cheap either. So.
A question from Tony, who is who's virtual. Go ahead, Tony. You can unmute yourself and ask the question.
Hey, good morning, Craig. Tony Verflute with the Crawford Clipper Ditch Company. Thanks for the concise and really good presentation. One thing that I will throw in, and you may not have mentioned, is, and we've run into it. We didn't run into it, but we were aware of it when we were putting our system in, was that we needed to be very careful about proprietary software and proprietary systems, locking ourselves into a company that, and we've all seen it with computers and phones, that once you've got it, there's not a lot you can do. You're sort of at their mercy. If you do find yourself in that situation, I'd recommend that you have a company that's definitely has some longevity, that's been around for a while. But there's always a chance that you'll get a company that's starting up and they're going to lock you into their system with proprietary, again, software, hardware, and you find yourself in trouble if, God forbid, the guy gets hit by the bus and it's a one-man company. You're kind of out in the cold.
Yeah.
So I just want to throw that in. Thank you.
Awesome. Any other questions? I mean, I can cover one other application I've seen recently that I don't think LaRue Creek water users are in here for the afternoon, so I won't be like doubling up what they did, but they recently implemented just a pretty basic one-site system that has helped them immensely. From what I've been told, is they have about 30 reservoirs up in the LaRue Creek Basin that they do releases from to the creek. It passes down the creek, then they have a canal that pulls the water back off the creek to one key reservoir at the bottom, that then they make releases back to the creek for. So they're kind of balancing down there, all the reservoirs released to there. Then they have that one main release point that releases to the creek, which then goes down a ways until they pull out again to their delivery canal. Well, the problem is the timing of that system is, if they change something at the reservoir, let's say the farmers want the water obviously like 6 to 8 in the morning. It's nice if that's when their water arrives at their head gate. To do that, they need to make their release from the reservoir at 1 o'clock in the morning. Well, the water commissioner or the ditch rider doesn't want to go up to the reservoir at 1 o'clock in the morning to change the flow rate. So they change it usually at 6 p.m. Well, you're wasting that water then. There's about 6 extra hours there where it just flows past the gate because no one's there to open the head gate when the water gets there at first. So they were just, I mean, water's getting wasted. And when it's storage water in today's climate, that is huge. And so what they did is they automated that one gate on the key reservoir. They didn't need to do all the reservoirs because their reservoirs all fed to that one point. So, but where their key regulation point was is that reservoir. So they just automated the gate and a flume at the outlet of the reservoir and were able to save a significant amount of water, is my understanding. So that was a very good, simple application that, I mean, you just add up even the time savings up and back to that reservoir where they can now program that gate to open at a certain hour. It saves them quite a bit of money.
Are there any case studies locally available that have been done?
Like written case studies.
Well, on that one, Paul can tell you how much water was saved on that Little Creek. And also the town of Hotchkiss paid for half of it, which
Okay.
helped the ditch company, you know, afford to do it.
Paul Schmucker.
Yeah.
Yeah. And that was, I know he was,
I mean, he's had serious issues with it as well.
yeah, I know. I haven't followed up with him on all of them, but
But he has a number of how much water was,
okay.
what they figured they saved on that.
And I will say, anytime you implement one, there's gonna be hiccups, that especially the first week or two as you're working the bugs out of the system. I mean, you kind of, I mean, it's just like when we go in and pipe all these canals. I mean, there's always some things you weren't thinking of maybe, or surprises that you gotta maybe deal with. And so there's a learning curve when you make changes like that to the system. But I think once you kind of get your legs under, because you guys, you're a year in, it went in last.
I think it went in last spring, yeah.
Yeah. So hopefully work through some of the kinks that year and smooth things out for the future, but.
Have you seen anything along the Cave City lines, at least for more than a year or two of documentation within Colorado? Does Applegate have anything where they've gone back and taken, you know, here's where we started, here's what it's done
It
over a
could be a
year?
good question for the locals panel discussion around, but did you have something to add, Gary? No.
Yeah, I recently, or a couple of years ago, the NRCS funded a CIG grant for, I think it was a well monitoring, maybe a stockwater pond monitoring program in eastern Colorado. But it did break down costs and time savings for the ditch company. You know, saving on fuel, labor costs, those types of things, and calculated that. So that information's out there. And I think it was someone who worked with one of the consultants, Bruce.
It's by Bruce.
One of Bruce Bates' colleagues that led that effort. And I think I have that information in some file stored away somewhere, but I can find it. My other question, maybe I missed it because I came in late, Craig, was, have you worked with LoRa Technologies, the low frequency, long range radio systems that can do similar? It's similar to what a cellular network can do, but it's a little bit less cost intensive. We can add controls and monitoring flows and head gates, and it's good for like single farm systems or one irrigation district.
Okay. Is it LORA or is it?
Yeah, LORA
Okay.
or LoRaWAN technologies, but TU is used at just connecting a flume, like a check structure in a ditch to a pressure sensor in the ground. So water's here, flips a gate, and the water goes down to the next system. And we've done quite a bit of work on Bill Trampy's ranch in the Upper Gunnison using that technology.
I was also going to add that through the Lower Gunnison project, you know, where RCBP funds were used for several of the projects that we'll be talking later today. The River District put together a final report on that project. And there's a table there, and this report is available through the River District's website and also through the Gunnison Basin Roundtable. But there's a table on estimated average annual benefits, and it's divided into reduced travel costs, O&M savings, producer benefits, and maybe that can help also with some of those questions. Any other questions? Well,
Am I
Craig,
off the hook?
yes, thank you so much. All right. Thank you, Craig. That was really great overview. And where'd you go?
I'm here.
Oh. And so the next panel, next presentation that we have is the Grand Mesa Software and Water Efficiency Project. And to start us off, I would like to invite up here Bob Morris, who's the president of the board of the Grand Mesa Water Users Association.
Thank you. Grand Mesa Water Users, on the south side of Grand Mesa, we have a little over 100 reservoirs. And they're tough to get to, time consuming. All of the conditions that Craig just went through, we have them, the bad conditions. And so 3 or 4 years ago, we started looking at all these problems. And as most of you realize, water is just like your bank account. You've got to have accuracy, and you also have to have timeliness of the facts. And so the accuracy is a big problem right now because of droughts. You've got to account for every drop of water. And then in our case, in the Service Creek Valley, we're getting a big influx of new customers just because land is being split up. And then, as I mentioned, the drought has caused a lot of problems. And then labor. It's getting tough to find labor, especially for seasonal jobs. So 3 or 4 years ago, our board began the process of getting this project put together. We're just starting the first 2 years of a 4-year project, and it is in 3 segments. First, we'll do capacity surveys on the reservoirs so that we know exactly what we have there. And then we will put in sensors on the reservoirs. Initially, we were only talking sensors on the reservoirs, but now we're looking at sensors, reservoirs, and parcels below them, and some of them parcels above. And excuse me, in the future, especially on our pressure reservoirs, we'll be looking at automated pit gates. And then the last part, you can have the sensors and be sending data to your office, but unless you have the computer software, it really won't do you much good. So that's our 3rd segment. And so with that, I would like to introduce Denise Jackson. She's the lady that keeps all of us straightened out.
Thanks, Bob. So Bob Morris is our fearless leader. He's the president of Grand Mesa Water Users. But one of our board members left, Paul Meyer. There is a total of 7, and they are just stellar. It is their vision to modernize our system. That's the reason why I'm here. It's the reason why we have our efficiency project. I would also like to give a big shout out to Amy Moyer. She's the director of strategic partnerships with the Colorado River District, and she has been amazing, wonderful. And she has made their grant process seem almost painless. So my name is Denise, and I am the current administrator of the Grand Mesa Water Users. I answer directly to Bob and the board. But in essence, I also answer to all of the reservoir owners within the Surface Creek Valley. Why? Well, because we manage a database that has their private reservoir information, and we're responsible for keeping accurate accounting of their water and their water orders. So Our office administers, as Bob mentioned, 100+ privately owned reservoirs on the Grand Mesa. That water is turned out of the reservoirs into 7 different drainages. And from there, it goes to several hundred ditches to 2,000 and counting shareholders and 4 municipal water companies. So does it sound complicated? It is. There's a lot of moving parts. There's a lot to keep track of, and accurate accounting is an absolute must. We have a very finite resource. So in the not so distant past, we used pencil paper ledgers to keep track of ownership, to keep track of water orders. But this was when all of our owners, the list of our owners, could fit on one sheet of paper. That's not the case anymore. So we also have hand-drawn maps which illustrated the drainages, typed sheets that made up the decree call lists. And all of the computations were done by hand. And do you think that mistakes happened? Yeah, absolutely. Probably more than we want to recognize, right? So I still love and use the old maps. I do, for illustration purposes, but thankfully for the past 20 years, we have had an Access computer program which tracks the ownership information and also the debits and credits associated with their water account. But its functionality is waning and it's fraying around the edges, and I'm not sure which day it's going to crash on me and I'm going to be back to the pencil and paper method. So we're looking forward to the future with our efficiency project. And as Bob mentioned, it's a 2-phase, 4-year project using drones to collect the accurate capacity charts, then installing sensors to collect the real-time data of the gauge heights and the stream flow rates. And finally, a custom software that integrates and models all of this with an interactive water ordering system, and hopefully with an app, right? Because everything's on an app. So in my opinion, an online ordering system can get everybody involved, and it also has the potential to put the responsibility back on the users and make them a part of using their water efficiently. So let's talk about the benefits, because that's what everybody really wants to know about, right? Our irrigation season ends October 31st. And I need the gauge rod readings as of that date to know the carryover. Carryover is the amount of water remaining in the reservoirs at the end of the season. If we get numbers too early and there's a heavy rain, the owners might not get proper credit. If we get numbers too late, then a senior filling decree might be injured. So right now, we are in our fill season, which is November 1 through March 31st. And we need sensors to monitor what's coming into the reservoirs. If it's a good water year, then the reservoirs spill. There's sufficient water and everybody's happy, right? But that hasn't really been the case the past few years. So inevitably, there's a call that's placed by a senior water right owner. And that triggers a peg on our reservoirs. And all of our decrees that are junior to that senior calling structure have to stop filling until that senior is satisfied. Okay. So we also have our irrigation season, which runs April 1st through October 31st. And during that time frame, we want to constantly monitor our reservoirs. We have a very large concentration of high hazard dams on the Mesa. And we want to know where our water is, when, how much, all the time. We want to know that. And we've got some pretty industrious beavers up there. They build their homes in the spillways. They do it during odd hours and they really don't ask permission. And so sensors can alert us to any sudden change in the reservoir levels or the stream levels. We can set alarms and it can warn us, right? Something catastrophic might be happening. It can also alert us to an incorrect reservoir term. And our office is dedicated to timely, accurate delivery of our water. So what is the problem with needing all of this data that is date sensitive, right? Well, without sensors, we rely on humans to go get that information, to go get the gauge rod readings. And we know about humans, right? They get sick, they go on vacation, they transpose numbers, and their equipment breaks down. And the reservoirs on the Mesa, a lot of them aren't really easily accessible. So sensors will allow for the real-time data collection. And I am personally very excited to be able to push a button, get that information instantaneously accurate without all of those challenges. So without further ado, I would like to welcome Mr. Pierre Stormer. He's with Drone Mapper and he brings the DA in SCADA.
Thanks, good job. Good morning. My name is Pierre Stormer. I'm with Drone Mapper, a small company out of Cedar Edge. And for this project, we're providing two technologies that I'll speak to you about and show you some examples. Oh, sorry. I'm dealing with the light. Okay, so I'm going to be discussing data acquisition. The back part is SCADA, but it's an important function to do. The first thing that Denise mentioned is that we do reservoir capacity surveys. So what that entails is, and here's an example, this is Hotel Twin up near Alexander Lake, and it's shown in this Google image full. The green dots that you see are a set of images collected via drone, and they have high overlap. The blue and white flags here, 6 of them, are precision ground survey coordinates. So what happens is we use the imagery and these known XYZ locations and produce a surface model through photogrammetry. That's a very accurate digital elevation model, digital surface model. We then use that 3D model to generate a set of contours at constant elevation. So you'll see that the brown lines up here is Hotel Twin Lake last summer when we flew it with the contours generated. The contours are then used to determine reservoir surface area and volume, which gives us capacity. And here's a model of what that data looks like. Here's gauge height, from 0 to spill, which is probably around 17 foot. And here are the associated calculated volumes in acre feet per foot of elevation change. So we use that model in another device that we provide, another technology called Aquabits. But before I go to that, people are interested in cost. Here's what if you had us do a reservoir survey, we would charge you somewhere between $500 and $2,500. And it's dependent on the reservoir size. The larger the reservoir, the more dollars. The number of survey control points, those are the precision ground control targets that we have to survey. And then how easy is it to access the reservoir and then get around in the reservoir to set the targets? That's what controls that. If you want to do this yourself, if you have your own drone, here's some software tools that we provide or can provide. The photogrammetry software is called Remote Expert. We produce that, we've written that software. It's available at dronemapper.com. And then for GIS, for contours and volume generation, we use Global Mapper. It's licensed for about $500 or $600, and you get that from Blue Marble Geographics. Excellent piece of software, very affordable and accurate. Next chart. Okay, so this is Aquabits. This is there's a embodiment of the hardware. This is the next generation. The electronics enclosure to NEMA enclosure for weatherproofing. Lithium lead phosphate battery. A 10-watt solar panel, and then a couple of different versions of pressure transducer that we use. So how this works is we serve 2 applications, a flowing water application in a flume or weir, or a still water application in a reservoir. Each are equipped with a sensor. In this case, this is shown sort of slanted near or at the invert of the reservoir, so we can calibrate the zero elevation reference. Likewise, with the flume, the sensor is sat right on the floor of the flume, and that's our 0 point. And we measure gauge height in both applications by sending a digital signal to a microcomputer or PLC. This electronics includes the solar panel, the battery, the microcomputer, the immersible sensors, as well as your selection of either a cellular or a satellite communication modem. We'll go into that, or I'll show you, we can talk about that later. Okay, so here's example data that we've been taking since, I think it was last summer. So I think here we show a time record for Hotel Twin Lake from July through January. I think it's mid-January. The data is provided at 6-hour intervals via SATCOM because there is no cellular communications at that location. And what's interesting about this reservoir is that with no precipitation, which occurs through a lot of this time frame, there's a natural ingress. So this is being fed by springs, internal springs. And you can see that even in the winter, after the ground freezes, you still have the same natural ingress, plus or minus, it's around 0.4 of an inch per day. And it changes just a little bit. A couple other interesting features. This is in December. These are snow events. So remember the snows we got mid to late December? I'll show you some blown up data on this. It's very interesting. We didn't go out to February, but I have data on that as well. So that's Hotel Twin Lake. This is Park Reservoir. This is a larger reservoir. And it's got a much longer time frame. So you can see data from October or late September when we did the install out through mid-January or so.
Well, it's a live sensor, yeah, it's live. So we're collecting data now.
Yeah, we're collecting, again, this is 6-hour interval data, also transmitting with satellite communications modem. It also has a natural ingress. This is about, Hotel Twin was about 0.2 of an inch per day, and this is about 0.4, so about double amount of water, but it's a much larger reservoir. Okay, here's some examples of open channels that we've outfitted with instrumentation. This was our first one, Big Digit Cement. It reports at 2-hour intervals, and it is fortunate that it has a cellular signal modem, so the data costs are a little bit more affordable. These two went in the summer of last year. Harts Basin Pipeline, that's a 9-foot suppressed weir. The instrument's shown here. And there's a stilling pipe that we put the pressure transducer. In this case, the pressure transducer does not sit on the floor because it's a stagnant still. It sits at the 0 elevation of the weir blade. So we set that to calibrate it. And this is a 2-foot partial. It also reports via cellular every 15 minutes. Next slide. So here's the gauge height recording for Harts Basin. Looking down, here's the intakes. These two big 16-inch pipes are the intakes, 9-foot weir. Here's our stilling tube, if you will. Electronics box is open, and the pressure transducer sits on this wall right next to the staff gauge from manual reading and provides this data through that period at 15 minutes. Okay, sensor costs. Right now, if it's cellular outfitted for communications, you're looking at about $3,000, possibly less depending on logistics. $10 a month for data, cellular data. The SATCOM version uses the Iridium constellation, and they're very proud of their rates for data. They start at $20 a month for 6-hour interval. Keep in mind, this is 15-minute interval or whatever you need. If you go to 30-minute interval data, this jumps to $40, $45 per month. It's pricey when you start putting in a lot of sensors. So this is one of our biggest concerns on the project, is that as we outfit more and more, we scale on the Mesa, data's gonna eat you up unless we can find another. Yes, sir.
Is the cellular a line of sight type communication system?
Well, I think it would be because it's 4G LTE. It's either provided by AT&T or Verizon,
Okay,
or sometimes T-Mobile. So somehow they're getting signal in there. Not sure how they're doing it. But we have a spectrum analyzer. We can go up and do a scan and see what service providers are here before we select the modem for the instrument.
okay.
And somebody was mentioning LoRa. LoRa is a technology that can provide scalability and affordability. So if you go, we have 300 reservoirs on the Mesa, probably another 300 or 600 weirs and flumes that could be interesting to outfit. LoRa, you can scale and keep the per sensor cost down to maybe $1 or 50 cents, something like that. So it's something we're looking into as we see this satellite communication data problem. We'll find out if we have to go that way. Okay, so here's some interesting data. Well, how come the top's coming off? Well, that's okay. Well, hopefully you find this interesting. This is for the month of December last year. These are snow events. So what you're looking at is snow water equivalent. And there's a couple of data sources here. Snowtel at Park Reservoir. So site 682 is where I got this data. And that's the red or cyan color. The next one down is our sensor in Park adjusted for the ingress that we talked about, the natural ingress that you see daily. So this should be apples to apples comparison, as well as Hotel Twin, which is the green dots. And you can see that the temporal trends are pretty good. They match each other temporally in terms of when the snow events happen. The magnitudes are a little different. So, you know, Hotel Twin and Park are separated as the crow flies about 5 miles or so. So the thought is here that, you know, the east side of the Mesa near Park got more snow in this event, or this set of events. But anyway, the discrepancy between what we report with Aquabits versus what Snowtel reports is about 3 inches. So it's a sizable difference. We don't know where it comes from.
How are you measuring snow water equivalent? I thought you were measuring
Pressure. So if you have a water column and you have a hydrostatic pressure sensor senses how much water, how it grows.
Right, but that's in the reservoir.
Correct.
But
These are reservoir sensors.
okay, you have it in there as snow water equivalent.
Because it is. You have a water column and there's caveat. Then you have an ice layer, then you have snow, no matter what the density. If the water column is in contact with the ice, you're measuring water. Doesn't matter what the density is. It can be 9% less on the ice layer, 20% less in the snow layer, still water. So it's all weight. It's what we're doing is measuring weight. Yes, sir.
Are your targets floating out of the reservoir?
No, you mean for the drone?
Yes.
No, the reservoir must be empty. So we can map the basin. We can't see through water when we fly it. So those targets are on bare ground after the reservoir has dumped its water. And then we correlate the image to the position of the targets, what pixel it occurs in, and that's how we provide very high accuracy on the maps. Very low elevation error. Sorry. Okay, the last data slide that I have is this is last week's event. Blue is Snowtel. This is for just Park Reservoir, snow water equivalent. Temporal trends, and I flatten this again. Although Snowtel has a little bit of ratty noise in it, I flattened our data to take care of the ingress, you know, the normal ingress. Just look at SWE. And you can see in this case, we're still consistent. We're lower than Snowtel, but it's about a ½ inch difference in this particular case. I think that's it for me.
What's how far away is the Snowtel site from this reservoir?
It's down on the west corner of the lake.
Probably about a half a mile.
You think it's that far?
Yeah.
Yeah.
Yeah, because
Okay,
this
well,
is,
yeah, you guys go up there.
yeah, the snow tail's up by, Elk Park. Yeah,
Okay,
it's a little bit up.
so that's all I've got. I'd like to introduce John Walker. He's gonna say, talk about the SCA and how he's gonna utilize this data as we outfit the mountain more and more.
Thank you, Pierre.
You betcha.
My name is John Walker. I founded a company called Walker Water. Walker Water is a technology company focused on the development of software tools and tech and services for irrigation water management, irrigation management. We are a small company, so there was mention of not using startup companies, but I am a startup company, so please give me a chance. All right, so what we're looking at here is just a cartoon of the global water cycle. There's a lot of complicated terms in there. A lot of effort is being made to model this water cycle. The USGS and the Division of Water Resources in the state of Colorado, if you go to their websites, they're putting a lot of effort into trying to model these systems. Walker Water is not quite that ambitious. What we're going to try to model and get a better quantification of is evaporation in our reservoirs, inflows in our reservoirs, okay? If we put a sensor in the reservoir and we put a sensor in the outlet flume of the reservoir, we know the outflow, right? The commissioner went up there and turned, let's say, 10 feet of reservoir water and 2 feet of flow. So we have 12 CFS coming out of the outlet. Using that, we can calculate the exact level that should be changing in the reservoir. The water should be coming out of the reservoir. Let's say that the water doesn't come out as much, the level isn't changing as much as we think it is, right? Well, then we've got some inflows coming in and we can calculate what those inflows are if we have those sensors. Let's say the water is not, the level of the water is coming down faster than we anticipate or calculate. What does that mean? It means we've got water coming out of the system somewhere through evaporation or seeps or something else is going on. So we're going to endeavor to quantify that. Right now, evaporation is taken right across the top of the board. So when Denise's office does allocations and appropriations, they take a certain percent of water right off the top of the reservoir for evaporation. Is that number that they've been using historically accurate? It's probably not accurate. If we have a cool summer, there's not going to be a lot of evaporation on the mountain. If we have a hot summer up there, it's going to be more. Some reservoirs are going to evaporate more than others. Some reservoirs are in the shade, some aren't. So that one fits all doesn't fit, okay? And I think the commissioners have been using that water as pocket water for all these years, right? Keeping it in their back pocket in case something goes wrong. They'll have it available for them. Okay, so we're going to attempt to better quantify those types of events, precipitation events, evaporation events in the reservoir. But there's also another set of events that occur. So we have long ditches that we deliver water down, and those ditches incur transit loss. There's shrink in those ditches, right? And as a user, I'm also on the board of directors of Grand Mesa, but how is shrink computed? Well, typically it's 1% per mile, all right? Let me give you a couple of examples. On Surface Creek, when we turn a lot of water into the creek, on occasion, the creek loses something on the order of 10 CFS. It just goes into a hole. Now, we don't know why that is. Maybe it's because we're putting more water in, the banks are absorbing some of it until they get saturated. Maybe because we've raised the level, the trees are starting to drink it. I don't know. We don't really know. But we do know that the creek will lose 10 CFS, and we don't know how to predict it. We don't know how long it's going to last. So we'd like to do a better job of quantifying that, trying to get an understanding of what's going on. Let me give you another example. I get my private water delivered along a very long, dry ditch. In fact, Denise says it's the worst ditch in the valley. And she gave me crap for buying that piece of property when I bought it. But the problem is when the ditch rider assigns an 18% shrink at my head gate, and I'm always like, why is that? That seems extraordinary, right? Particularly because I'm one of the first head gates on the ditch. Okay, so what if I had a sensor at the top of the ditch, had a sensor at my head gate? I can compute all the orders between me and, the top of the ditch, take that off the top. I should know exactly how much water is sitting at my head gate, and therefore I should know what shrink is applied, right? The 18% shrink seemed really crazy. The other part of the problem with that particular story is the ditch rider happens to be the last guy on the ditch. He's a big rancher. So I would like to have a sensor and say, that's not cool, dude. All right. Denise mentioned aging methods. I am a water commissioner on the mountain, so I took these pictures last summer. And on the left, you see how we measure gauge height. All of the reservoirs up there have a gauge rod that goes down the dam to the outlet to the outlet pipe. Those gauge rods, some of them are metal, some of them are wood. The wood ones are supposed to float, but they've been up there for 100 years. They're completely saturated. They don't float. They just sit on the bottom. Each of those gauge rods is graduated with a 1 foot graduation, some of them are scratched on, some are handwritten, some have metal bands on them. Some of the gauge rods are metal pipes that are actually broken, right? So like, how are you supposed to measure when the pipe's sitting up in the air and this one's down here? So you can see that this way of measuring using a ruler is probably not real accurate, especially if there's any wind that day, which there's always wind on the Mesa. You can't really get an accurate measure of the gauge height. The middle picture shows me measuring flow rate in a V-notch. Okay, so one thing to notice immediately is I'm not doing that properly. Apparently, you're supposed to put a stake about a yard upstream of that V-notch at the same elevation as the V-notch and measure it there, right? It's kind of like a little stilling pond. But inevitably, you can't find that stake. You got to reach over there. You're going to fall in that cold water. So we just stick it right there, and then we use an equation and convert that decimal inches to a flow rate. But that's not very accurate. And then lastly, on the right, I was standing on a flume. I intended to output 2 CFS. And fortunately, the volume is turned down because I let out some expletives when I realized as I was standing there reading the staff gauge, I had forgotten my weir card, right? So it's a 9-inch flume, but what does 0.32 inches on the staff gauge translate to flow rate? I don't have all that memorized, right? I'm not up there. I haven't been up there long enough to memorize that. So I took a swag, right? I stood there and I was like, how much water is coming out, right? I guessed. But for the rest of the day, all my turns that day were guessed. I wasn't going to go back down the mountain and get my work done. There's no cell phone coverage up there. There's no internet coverage up there. So I made guesses all day long. And imagine if Denise had software and a sensor, she would have known that I'd made an incorrect turn, right? Immediately. All right, moving on. Denise talked about old documents. These 2 documents here, the one on the left is the ditch priority. It's essentially the priority of the ditches on the surface creek and the amount of water assigned to them, the volume of water. So when a call comes on the creek, we use that document to determine what head gates need to get shut off. The document on the right is a call list for a reservoir. There's a reservoir in our area called the Fruit Growers. It's the number 24 priority. And when a call comes on from Fruit Growers, we need to know what reservoirs above it to peg, as Denise had mentioned. So that's the call list. And so these are the 2 documents that are currently used to do this sort of thing. Grand Mesa water users hired Walker Water to do a feasibility study of putting this stuff into a software system to make it accurate. Because you can imagine when a call comes on the creek, well, let's say a call comes on a reservoir, we have to go up and peg reservoirs, calculate volumes, bring that information back down the mountain, compute the volumes in each of the reservoirs that are going to be affected. And do you think mistakes can be made in that computation? You bet. All right. So let me just go through and talk about what we're looking at here. So on the far left, and I have this software here on my workstation here. If anybody wants to see it live, I can demo it later. On the left are the list of the reservoirs. I've selected the Park Reservoir here. And essentially what comes up down here is a list of the reservoirs that are junior to the senior most decree. So I've selected the senior most decree. what you're looking at here are tanks that represent each of the reservoirs. This is the tank for Park. It has 3,000 some odd acre feet in it. The cyan color is the carryover from the previous year. The blue is water that's coming into the reservoir on top of the carryover. And the reason I have this now on Park is because we have a live sensor, right? So what you see in that dark blue is the water that's come on in there since October 31st, okay? And that is live data. So this is saying how much water is coming in to satisfy the senior decree. These brown colors indicate there's no water. This is yellow because I clicked on it, but this is the amount of water that satisfies the number 3 decree, the senior decree in the Park Reservoir. This is a decree that is junior to the senior, and this is the 3rd degree in Park. So Park Reservoir has 3 decrees, okay? Now, when I clicked on the senior decree, it pulled up all the reservoirs that are junior to Park or junior to that specific decree. So Peak, Military Park, Blanche Park, Peak again, Elk Park, Bella, etc. Notice the carryover in each of those reservoirs. That carryover is protected. That water cannot be called out. That's why carryover is really important, right? And that's why it's important that we get those carryover numbers accurately in a timely fashion, because we can injure somebody if they're not computed properly. Okay, so what I've done, the software is graying out various decrees and reservoirs, but the ones that are not grayed out are the decrees that are junior to this number 3. So Peak, any water in this would be called out. There is none, it's too junior. Military Park, the same situation. Because they had so much carryover in Military Park, this junior decree is not affected. Blanche Park, all of its water would be affected. Peak, this decree in Peak would be affected. So if there was water in this reservoir, it doesn't have a sensor. So right now it shows that there is no additional water, but we know there's water in Peak. That water could legally be called by Park if the number 3 decree was not filled at the end of the fill season. Okay, so this is a really powerful tool. I mean, it saves us water, right? It saves us water because we are now, delivering water to the appropriate calling structure, and we know exactly how much water is supposed to get there. In the past, it's always been a kind of, is it right? We don't really know. So this is a cool tool. All right. The next thing that I want to show is, this is something I'm really, really proud of. This is a 3D visualization system. Basically, I've got the Earth's elevations in a 3D visualization system. What you're looking at here is Western Colorado. It's a little bit hard to see on this monitor. The resolution is not great, but this is the Grand Mesa here. Obviously, the Colorado River, the Gunnison River, the Uncompahgre River, the Smith Fork, the North Fork, Plateau Creek over here. These are all the reservoirs sitting up on the Grand Mesa, and the drainage is coming down. Redlands Mesa, LaRue Creek getting on up in here. What is being drawn now in terms of color and line thickness is the flow indicated by sensors. So my software reads all of the USGS and DWR sensors in real time and is showing what's in those sensors. So you will see some of the streams are brown. There are no sensors. We don't have sensors throughout this whole system here. We do have a few sensors on the mountain. There's a sensor up here on Surface Creek. And there's another sensor on Surface Creek right here. They're both DWR sensors. This sensor is active. This one says it's iced out, so it gives a null value. So I just set that part of the section of the creek to 0 because there is no sensor indicating flow there. All right, so all of the flow, the color that you see is what the sensors are telling us in real time. That's what's actually in the streams. All right, I'm going to flip now to what the software is modeling. Okay, it's important that we model what's in the creeks so that we can compare it to what the sensors are telling us is actually in the creeks, right? So how does the modeling work? Well, the modeling says, I know there's flow in all of these streams and creeks right now. We don't have sensors in them, right? But I know there's flow in them, and I'm going to estimate that flow based on what I know. If this is during the irrigation season, I can also show reservoir orders in here. And so we know what the commissioners are turning in reservoir water. We know what they're turning in flow. So we can essentially model what we believe should be in the system. And then we should compare that against what the sensors are actually saying is actually in the system, right? So the software is going to keep track of the model flow rates or the model volumes that are in the creeks, compared to what the sensors are saying, and turn on alarms or notifications if those things are significantly different. So let's say we have a rain event. The sensors are suddenly going to show that there's more water in the ditch or in the creek than the model is, right? So the software is going to notify us. It's going to say something's different. Oh, well, we know it's a rain event. There's no reservoir that breached. We don't need to panic. Well, what about the opposite the situation? Let's say the sensors are indicating that there's a lot less water than the modeling is suggesting. Well, what do we think is going on? Something has happened that is causing the river to go down. Did somebody put a pump illegally upstream, right? Somebody stealing water, or is there something else that's happened? So this is a live dashboard. I've developed this to be a dashboard that's going to sit down in the Grand Mesa Water Users Office. Craig showed some complicated dashboards. This is essentially going to be like that. The software is going to have multiple different ways with graphs and pie charts and different ways to visualize the data. Denise mentions users come into the office all the time and they say, where's my water? What's going on? How much water is in my reservoir? And she can never really tell them, right? But now she's going to be able to tell them and educate them on what's going on. So yeah, that's what Walker Water is doing. Putting all of this into a computerized control system. So yeah, thank you. With that, I'm going to turn it back over to Bob.
Thank you, John, and Pierre, and Denise. One thing that we didn't mention, we have a little over 100 reservoirs. We cannot drain 100 reservoirs just to put sensors in 1 year. We almost could last year. It wasn't my choice. So that's why we have a 4-year program. Hopefully we can manipulate different reservoirs across the board, get this one emptied, and pull some water from another. That way we won't lose it. Are there any other questions?
There is a question that came up in the Q&A when Pierre was presenting. So Andy is asking, when you determine a GH volume curve with a drone, does it account for silt in the reservoir? How does your curve compare to historic data for that reservoir?
So let's see if I can answer this. If you fly with the reservoir drained, you are sampling the surface in that time frame. So if there's silt, it'll be visualized as silt. If there's logs, rocks, etc., the whole surface will be characterized. So the answer is yes, we do account for silt, and that's why you want to look at time change. And that's why you really want to have precise ground control, so that you can compare pixel to pixel and say, I can tell you exactly where the silting occurs at this channel, and you have an unstable slope. But you have to have meaningful change detection. So it has to be done. Pixels are aligned from last week to 2 years from now.
So
that's how you tell. That's how you could measure silt.
So if you fly the drone over the empty reservoir today, and then let's say in 3 years, would you fly it over again to see like how much silt?
Absolutely.
Okay.
And you'd use the same targets, same control points, so that everything aligns to the pixel level. The second part of that, our curves don't align, and this is a database of about 25 reservoirs roughly that we've flown in the last 5 years. Some of them are spot on with old records, and the old records can be 50 to 80 years old, or these are old surveys. We're high in many cases and we're low in many cases. So it's a mixed bag. But we believe our data. We're trying to make these guys believe our data.
All in all, it's been pretty close. One reservoir, medium size, I think we were within, 5 acre-feet of the 1950 survey. Another reservoir that was built in the 60s, we actually gained some water in it.
Gain 100 acre feet.
We must have washed the silt out. But all in all, it, give and take a little bit for each one, but it's come pretty close.
Yeah, Colby, a couple of interesting cases, Colby Horse Park, which is pretty remote, and up near Leon, which is also remote. The client was certain that Colby Horse Park silted in. And when we flew it and did the volumetrics, we said, no, you actually get a little bit more volume, acre feet than you thought you had. And vice versa happened on Leon. We said you have less water there. But Leon has a huge dead pool, and that messes with photogrammetry because you can't, so there's some errors in everything you do, but I think it's fairly low.
Does anyone have any questions?
What's this cost for the whole project over 5 years?
First 2 years, and essentially we'll be putting in half the sensors and most of the programming. And the first 2 years, 440,000. Last 2 years will probably be about the same
Did you get grants?
for the first 2 years from several places. For grant.
What's the average cost of flying the drone flight over a reservoir?
Pierre?
The average cost for Grand Mesa, with their sizes, it's about $750 to do the math, do the capacity math. For their average, we've flown some big reservoirs, like 6,000 acre foot.
Overland, yeah.
Overland was a big reservoir. That was $2,800. That's the most we've charged. But it took a better part of a day to get all the data, and the logistics were terrible.
Yeah.
Almost got stuck in the bed a few times. Hope that answers.
And then Andy is asking, do you have to update your curve with the state?
That's probably you guys. What do you do with, when I give you
The
new
state
table?
updates theirs.
Well, they do
Yes.
with our data.
Yes.
Okay. It's funny, the state 5 years ago, 6 years ago said, we can't accept this technique. It's unproven. And then about a year or 2 years ago, they wrote a memo saying, this is a well-accepted technique. So it changed, they got educated, I guess.
No, and I think it's a challenge too with the changing technology. People are used to doing something one way and they have to, make sure that it suits their needs. And I think it's a work in progress too.
Yep.
Any other questions? Oh, yeah. Okay, well, thank you very much to all of our presenters. Guess we should give them a round of applause. And for our next session, we're doing a local projects panel. And before we get into that, I do want to give a shout out to my colleague at the River District, Dave Kanzer. He, has been working here with many of you and in this basin for more than 20 years. And he's moving to bigger things within the River District, but all of these 4 projects that we'll be talking with us next were funded to some extent with RCPP, the Regional Conservation Program, Partnership Program with NRCS as a part of the Lower Gunnison project. And he was really instrumental in all of that effort, and that piece of the funding ended in July of last year. So thank you, DK. He's not listening to us today because he is out of the office, but I really do want to thank him for all his work. And so it is my pleasure to introduce and invite up front we had a shortage of chairs because so many of you signed up, which is great. So I'll ask the panelists to bring, and I can help. We'll just bring a chair for each up here. But the first one is Alan Distel. He is the president with Bostwick Park Water Conservancy District. I guess I'll introduce the four and then we can all come up. The second one is Steve Fletcher, who, you know, just he's here even though he has recent surgery done. He's the superintendent with Fire Mountain Canal. Third, we have Steve Pope, who is the new manager with Uncompahgre Valley Water Users Association. And the fourth is Tony. And Tony, you can turn your camera on if you like. And Vervloot. Hopefully I got that right.
There I am, bigger than life. Yes.
And Tony is with Crawford Clipper Ditch Company, and he is with us here remotely, but you guys can see him pretty good. So we can all bring a chair up. I'll also bring one. So that people can- That'll be good. And to start, let's pull up. Sorry. All right. So here we go. And hopefully, if you cannot see the slides, we're gonna go through some slides at the beginning, and then we can always turn the lights off if need be. But here are our panelists, and they each prepared a couple of slides just to run over a general overview of the projects they implemented, and then we'll go dive into a few questions and then do a question and answer. So Alan, you're up.
Bostwick Park Water Conservancy District and the Cimarron Canal and Reservoir Company.
Sorry, 1 second. I forgot to share the screen. People are not, sorry. Wait.
Cal, do you want me to hit the lights?
Sure. All right, now people. Let's move this thing here. All right. I think we should be good now. This will go out there. Okay. All right. Sorry, Alan.
With the help of the River District, what Raquel just mentioned, the Dave Cancer, because we're so remote, our system starts at Silverjack Reservoir. Really tough. There is no communications at all up in that area. So we decided that before we got into, remotely controlling anything, the first thing we had to do was get some type of a reliable signal up there. So we set up the main backbone for our system. It consists of 3 main towers and 2 intermediate towers. And this is all for high-speed broadband internet. And they're the base of operations. We've got 2 offices in our office building. We've got 1 operation office, which basically is the superintendent's house. We've got 1 room that is dedicated to the servers to keep track of all this data that we're collecting in there. We got a satellite office. It sits about approximately a quarter of a mile from our main river diversion head gate in there. And it basically is a connecting cabinet which connects the radio signals and fiber optic cables and switches everything and keeps that all running. We bought a private link through an internet provider so that this is a private link. It's like having a private telephone line. the national or international internet could go down and our system will still communicate in there because it's all connected to this one system. We've installed fiber optic line. We put in about 2 miles of fiber optics. And the connection in areas that we put this fiber optic is where we can't get line of sight for radio communication. Heavy trees in the bottom of canyons and that type of stuff. So that's our main backbone for the system. This system, with the help of the River District, this has cost the district and the Canal Company just about $500,000 to put this system in. And then since we've put the system in, we put in a new ramp flume. It's got level sensors. They're connected to the control gates that are in the river diversion head gate. And this will maintain the level of the canal, no matter what the flow of the river is. So it doesn't matter whether we're pulling storage water or whether we're on overflow, our head gate will stay the same. It'll divert the same amount of water all the time in there. We've automated control gates. We've put in 5 cameras at the head gate. We can actually, from either the office or anywhere, via smartphone, computer, whatever, we can look at those 5 cameras and we know what's going on. If you want to check the accuracy, if we've actually got a camera that is pointed directly at the staff gauge and the ramp flume. So you can get a visual monitor of what that's doing if you don't believe the reading you're getting. And there we've got a head camera that is pointing down at the grizzly bars in front of the head gate. So the superintendent can look at that camera and know if something is plugged up on those grizzly bars, and if it is, what kind of equipment he needs to have up there to remove it. We've got 2 cameras at the main Silverjack Reservoir, and these are panning cameras. We can pan the entire reservoir to see what the level is, or if something's kind of goofy up there or something. We can rotate that camera around and we can actually point it right at the dam house. And the Bureau of Reclamation really likes that because they're really high on security. So if somebody is doing something up there, they're on camera in there. At our head gate, we put in one. We had problems with people messing with some of the equipment up there. So we put a camera at the head gate in the parking lot that whoever's up there, that they're there because they're on camera. And with our service and everything, this is recorded. So we can go back, somebody messed with something 2 weeks ago, we can go into the server and we can pull up the camera feed from 2 weeks ago and we can see exactly who was there. We've got flow readers at the end of the Cimarron Canal, and we've got a flow reader at the end of the East Lateral. The East Lateral is our furthermost location. It's our actual at the end of the system. And there, the flow reader at the end of the Cimarron Canal is where the canal splits for the first time. And there, so we, like was mentioned before, we know how much water we're diverting at the river. And with the flow reader at the end of the Cimarron Canal, this canal is 23 miles long. We know how much water we're losing through the two, comparing the two minus the deliveries. We know what our transit losses are. We have an automated trash cleaner at the end of the Vernal Mesa Canal, and there's no electricity there. So what it's equipped with is we actually have the paddle wheels. It's a rotating screen trash cleaner, a traveling screen trash cleaner. We use the paddle wheels that's running the this rotating screen is actually powering like a truck alternator to keep the battery charged. That's how we produce the electricity for it in there, and it's all automated. We've got Wi-Fi calling and high-speed internet at the Silverjack Reservoir, which you're up there at the reservoir and he needs to get in contact with somebody to make an adjustment on one of the controllers, or they need something, or you need emergency services. Well, you Wi-Fi calling, you can call right out up there, just like you're sitting downtown. And we've also got that at the Riverhead gate. And that's pretty much that's the equipment we installed after we got the main backbone set up.
Thank you, Alan, very much. And we'll move to Steve. I think, Steve, yes, Fire Mountain Canal.
Okay, before I go into some of the pictures here, I should have thrown a map in of the Fire Mountain Canal and Reservoir Company. The reservoir is Paonia Reservoir, which is quite a ways upstream on the North Fork of the Gunnison River. The Fire Mountain Canal actually has water rights out of the North Fork and LaRue Creek both. LaRue Creek's more down towards Hotchkiss, at the lower end of the canal, where just recently, over the last couple of years, we've piped that entire lower section from LaRue Creek to the tail end of the canal. And then the Paonia Reservoir is probably close to 20, I'm gonna say 20 some miles on upstream, or the head gate would be up there. And then the reservoir is probably about another 10 to 15 miles above the head gate itself. So the SCADA we put in, and it's an ongoing thing, is that we've had SCADA for a while up at the reservoir where we could remotely monitor and control the reservoir. That has been upgraded. The last year was kind of the first year we really got to kind of use the upgrades. We've been in the process of replacing the high pressure gates in there, so that's kind of been down for a couple of years while we were replacing them. But that we've got Wi-Fi up there now with well, I should say high-speed internet. They was able to get that up at the reservoir through Elevate, the DMEA. So we've actually got Wi-Fi calling availability up there and high-speed internet, which makes it nice. Because there again, it's kind of in a remote area. We did have a hard line prior that went up the telephone, so you had the dial-up internet, and it's got to where that's absolutely obsolete. I mean, we got to the point we were going back on Amazon and everything, looking for old laptops so we could actually use my dial-up with. And since then, now we've modernized. We can actually, just with like a flash drive, I can log into any computer anywhere, log in and make changes or see what's going on up at the reservoir at any time of the day, 24/7. And then the other part that we haven't this year, I'm hoping we get to do between the drought and the replacing the head gates. We've got the capability to tie into the real-time stream flow gauges on the Anthracite Creek and Muddy Creek, which back up just a little bit. Muddy Creek is the reservoirs on Muddy Creek. The anthracite comes right into Muddy Creek, right below the reservoir, right just below the spillway. The two Muddy and Anthracite form the North Fork of the Gunnison River. That's where the North Fork starts. So the Anthracite goes up one basin, which goes up towards basically Crested Butte, and the Muddy goes on up towards Little Clear Pass. So with this new technology we got, we haven't been able to use it yet because of everything we've been doing, but say during the summer, we get our big rain event up the Anthracite Basin and extra water comes down the Anthracite. It can actually send a signal to the gates at the reservoir and close Muddy Creek down a little bit to where the flow in the North Fork remains basically the same. We're able to, slow down the flows out of Muddy Creek or the reservoir and conserve water on that aspect. Our water rights, I might add, are kind of junior to there's a lot of seniors down below us. So we're called out pretty fast, and we rely 100% on the reservoir, on Paonia Reservoir by the end of the year. Usually, July, first part of August, we'll go into pretty near 100% stored water for the majority of the years. So it's real important that we can keep as much stored water as we possibly can. Like I said, we got water rights out of the North Fork and then our stored water, and then out of LaRue Creek, which we can feed the tail end of the canal. So with our pipeline, we've hooked up SCADA to where we can actually monitor what's coming out of LaRue Creek. We can remotely control that. This picture here is one of the laterals that come off of the new pipeline called the Patterson. We're tied into it to where we, know what we're releasing out it. And we control it. Let's go ahead and switch a picture. So LaRue Creek is up a canyon. The LaRue Creek Canyon, the head gate's up it, and then you come down. Our canal goes under LaRue Creek through a siphon, which the canal up here, and then comes up, and then the two of them meet over here. We needed a repeater for the two of them to talk together. So this repeater actually picks up a signal from the LaRue Creek head gates, and it can talk to the main head gate on the trash racks, and also send signals into the office. We've got a complete computer set up to where we get everything from the reservoir, the LaRue Creek, the main head gate off the North Fork, all come in together. This picture here is the LaRue Creek feeder. So it's a Rubicon gate. We can actually remotely control this gate. Usually in the spring of the year, we get some pretty good water out of LaRue Creek, so that allows us to back off on the water that we're having to put into the main canal up off the North Fork. As the water the last couple of years, this hasn't helped us a whole lot. LaRue Creek has been pretty stingy on its water, and we're down quite a ways on the water rights on it. So we haven't been able to do a lot. But this gate here will also maintain the flow. It's a Rubicon gate, the ramp gate or flume gate. And it'll actually maintain the same level coming out and then go over into the pipeline. That spillway there that you see at the bottom there, you go over and then go into the pipeline and go on down and then connect in with the Fire Mountain Canal itself. Like I say, this system's all new. This is the head gate on the canal, or not the head gate, but the trash rack at the head of the pipeline. As you can see, the canyon that goes in behind the backhoe there and then drops through the canyon and comes out on the other side. You can actually see on the far side there, the cut where they come in. Get up here, I'll show you. So our pipeline goes down under the canal or under the creek, comes up over here. This is the air vent to it. So LaRue Creek is piped all the way back up here and goes clear back up the canyon up there to where that water comes out. And that's just a picture basically of the inside of one of the boxes, kind of showing some of the little bit of the technology that's in there. What's really nice on this whole thing is that we can monitor what's going on at any time. We have the capability of controlling remotely the LaRue Creek, and what we can do with the what water we need at the end of the pipeline, our LaRue Creek. We can't remotely control the water coming out of the canal. We're in the process on our big picture. We're in the process now of looking at putting a reservoir, a regulating reservoir above the pipeline, to where we can have that bounce in there. Then we can be able to control what water's actually going into the pipeline there, or the canal, and be able to save water that right now, if the canal comes up or somebody shuts off, or LaRue Creek, for some reason, we wind up with extra water, it spills, it goes into LaRue Creek and we lose it, or vice versa. We lose water in the pipeline and now we're, struggling to bring water on down, 30 some miles upstream to bring it down. It usually takes a day or better. If we get the reservoir in, we'll tie that all into SCADA, where things will automatically keep that canal at the same level, and the reservoir will take the bounce to where gives us time to go up and actually again conserve water in the our main storage at Paonia Reservoir. That's just kind of a quick rundown of the whole thing. I know it's kind of down and dirty, but
No, thank you. And I guess the lights came up again. Next up is Steve Pope. And here's your map.
Thank you. Full disclosure, I've been with the Uncompahgre Valley users for just a couple months yet, so I haven't seen any of our SCADA operations actually operate. But in a prior life, I was with the Colorado Division of Water Resources for 25 years. And I have a fair amount of experience utilizing telemetry systems and working with SCADA gates to manage water, deal with water rights disputes, and manage augmentation plans. So this is a brief snapshot of our larger head gates. These are our major canals throughout the system. As you know, the Gunnison Tunnel diverts water and through the South Canal and delivers it to the Uncompahgre Valley. We have SCADA systems on most of these, all of those right now. And more importantly, in my mind, is we have a lot of telemetry throughout the system measuring return flows. We utilize water just like any irrigator as many times as possible, and we continually have water coming back into that system, and the need to measure it, the timing of return flows, and being able to track that water from one head gate down, knowing that when it'll arrive and what degree. As Craig had mentioned earlier, when you have someone that goes out and reads a weir, you know exactly what it read at that point in time. You don't know whether you're on the rising or the declining limb of a hydrograph, transit losses from one head gate to the other. So I fully plan to utilize any of our telemetry, and all of our SCADA is it's an information tool that helps us make better decisions, which will, in today's climate, both water rights and climately speaking, it's going to become much more important to maintain efficiency. Additionally, we have several projects where we're through selenium control, we're piping laterals. And anytime you make a change to your delivery systems, there is going to be a correlation on how water returns in the system. You may not be capturing return flows in the same places. You might be redirecting them. So we hope to utilize SCADA to lessen that learning curve and being able to map water as it comes through the system to best utilize it. Especially, these are a couple of these are just some of the major canals. This is the East Canal right there. Just some of the canals that we've installed some of our SCADA telemetry at. As Craig mentioned, we coordinate through the state engineer's office for our data. So we're using their satellite platform to push it up. That helps their water commissioners make some informed decisions as well for their administration of priority rights. So we work quite closely with them at, some of the tail ends of our canals. And it also will help us in all of our planning of projects of how to better utilize the existing water in the canal systems. One of the problems we have right now is, and I'm sure it is universal across the room, is, when you have bounce at a head gate, as you move down the canal system, that bounce just gets worse and worse and worse. And so if we can implement some telemetry through that, we can better track how water, we can minimize that bounce at the head gate by utilizing SCADA. And further, I guess, the issue, that's not one of mine.
No.
That's okay. And it's just the timing, these are big gates. Historically, you needed the personnel to run out there and adjust it. Some of them are in town, but it's nice to be able to have from the office a comprehensive picture, 35 miles of river, knowing what flows are where within our system and being able to adjust them simultaneously or plan. Again, being able to set up warnings and triggers that let us know which direction the stream is going is crucial in our operation. Let's see what else we got.
I think we're good, but
Okay.
thank you very much,
Yes,
Steve. And
absolutely.
we're going to move to Tony. Let me move to a table because this doesn't work very well. But Tony, can you see the slide?
Yes, I'm good. I think I can see it. Sorry for the delay. I was finishing my free lunch. So you guys got a free lunch in the background. I thought I may as well try mine. Anyway, I'll throw my
I
video
have a
up.
map here if that's easier for you to.
All right, what I'm going to do is I'm going to pull up my, which just disappeared on me. There it is. My note slide, and I can follow along. So my name's Tony Verflute. I'm a board member of the Clipper Ditch Company. We're all volunteers and we work diligently to keep our ditch in running order. I would like to start by thanking Raquel and her team for putting on the workshop. I think it's a big help. Okay, I hope it is anyway. So we've got 5 data collection points, and if you can, we can alternate between the slide and the map. But what we have is our base station on Young's Peak, High Point nearby, which allows us to push our data to the Young's Peak base station from our head gate, which is off of a partial flume, our pond inlet off of a partial flume. And again, these are sonic sensors on the partial flume, our fluctuation pond level, and then the Baxter manifold, which has our manifold with 5 meters for the Sperlin Mesa group. And we have tied into those 5 meters and we pulled data off of that. Our system is relatively new. We've only had it in play for about 8 or 9 months. So we're still learning, working on, the do's and don'ts and what works best for us, but it has been a very good system so far. We do have plans to add 2 more data collection points. The mill divider using ultrasonic, combination of ultrasonic sensors, Bigfoot sensors, and we're looking at actuated gates for this. And we're also setting up one at our Jordan Divide, which we're hoping will work with our we'll be able to actuate that also. So we'll reach our supervisory control at that point. So if you'll go to the slide after, I believe, let me pull this up and just make sure we're on the right page.
This one?
Yes, that's perfect. This should be the one on equipment. And our equipment that we're using right now is Campbell Scientific. We've got data loggers, 3 data loggers. They're small footprint. Basically, the data point is a 3-inch steel post housing and a battery charged by solar. The great thing about that is that it's very compact. It takes up very little space. And you saw a few of them earlier. In fact, the one on your agenda, the one that's a little color slide on the agenda, is actually at our fluctuation pond. That's the pond depth. We have 3 CR300 data loggers, data acquisition points, or PLCs. We have 1 CR310 and another CR1000. That's the one that's pulling data from the 5 meters. Our data collection points are pushing data to our base station using 900 megahertz radios. And then at that point, it's got a cellular gateway. So we're jumping to cellular, and then we broadcast our data via cellular so that we can pull it up on phones and don't have to find a landline or someplace to gather data. We can work off of cellular. The partial flumes have ultrasonic level distance sensors. So that's working off of partial. Our flux pond uses a pressure transducer for depth. And as I said earlier, and we had this I heard a number of people talking about it. At this time, we are not a closed loop, what I call a closed loop system. We are data acquisition only. We have not started any sort of actuation or supervisory control yet. So we are basically, I think by the definition, telemetry at this point, and we haven't gone full SCADA. All right, next slide. All right, general information. The Clipper ditch is over 21 miles of ditch and pipeline. That's what we have to maintain. And we have 1 part-time ditch rider, probably a similar story for most ditch companies in the area. Our system, our telemetry system has basically been put in to increase ditch rider efficiency. We're spending a lot of time driving back and forth between head gates and, on one end of the ditch and users on the other end of the ditch, and making adjustments. And as we said earlier, due to diurnal effects, rain, a number of all of the above and many more, we were spending far too much time not setting gates, getting water to our users efficiently and quickly. And so as soon as we had enough piping in, and we had the fluctuation pond, which was critical to our decision-making for telemetry, because we wanted to make sure that we collected water, any return flows or runoff water, we wanted to be able to capture due to rains or whatever, and not have it overfill the pond and push it down the spill. So all of our systems are set up with high flow, low flow alarms, and high level, low level alarms, which will, signal the ditch rider if he's not paying attention, or if it's after hours, that something needs to be addressed. Our system was installed by a company out of Logan, Utah, Intermountain Environmental. And we wanted a company with experience on ditch systems and small ditch companies. Again, we were working on a tight budget. We did have government funds, but we wanted to make sure we spent that money wisely. And so we went ahead and pulled this company in. We did look locally. And one thing I will caution is, and it's not a caution, and by the way, I do like startup companies, do not get me wrong. I threw that out there, and I did not mean to hurt anybody's feelings or be insulting. But we did when we started looking into this, we were late in the season because of funding. We had to wait to get funding in hand. So we did a lot of the upfront work, but we couldn't pull the trigger until we actually had the money in hand. And by the time we'd gotten around to the point where we were calling companies and saying, let's get started, let's get going. Well, we were right in the middle of irrigation season. And that's, you can imagine how busy these companies are. And so we found ourselves being the odd man out. We didn't have a huge project. It was a good project, but not big. A lot of the other projects had started, so the companies were committed. And Intermountain Environmental was really good to work with. They stepped up and said, we'll get you in. I mean, you may have to wait a little while, but we'll get you into the queue so we can start, getting you up and running with your telemetry and future SCADA system. So anyway, we had a few startup problems. We're still working out some of the bugs. Most of those problems were quickly fixed. And as I said, the system is very easy to operate. It's been a pleasure working with it. So we're looking forward to building onto it and growing it. And based on what Larry Applegate said, he's absolutely right. You got to be careful that you don't try to turn your Volkswagen into a Cadillac by hanging more stuff off the side of it. So we are managing how much of this, how far we're going to go once we start getting into a full supervisory control data acquisition system. Thank you.
No, thank you, Tony, very much. And now, Gary, could you turn the light on, please, for us?
They're on a timer, so they do their.
Oh, there. Thanks. Let me minimize this too. And here's, this slide will be up, but it's the contact information, the emails for our panelists. And we have some questions prepared, and then we'll open up for Q&A. So the first one is, what do you see as the biggest benefit of the system you've installed? And hopefully that's the reason why you installed, but I think not necessarily. So whoever wants to start.
Well, for Bostwick Park, the main thing that we wanted to do is we wanted to be as efficient as possible, because as you know, the Cimarron River, our head gate basically is almost the head end of the Cimarron River. And as Carrie Dennison will attest to it, the Cimarron River is terrible or notorious for getting too hot in the summertime. So with the inclusion of the SCADA system, we're able to better control the amount of water that is left in the river to maintain that level. We still got some temperature problems in the Cimarron River, but they're better now than what they were. The other one is reduced O&M costs. From where our field superintendent lives to the Silverjack Reservoir is almost 30 miles. In there, our ditch system, we've got 63 miles of ditches in there. So when he's way down on the bottom end of the ditch, he doesn't have enough water. If it wasn't for the automation, he'd have to drive all the way back up, either to the head gate or to Silverjack. And that's a 3-hour round trip. And he already had, when he first started working for us, he drove up there, I think 3 or 4 times a day, trying to get the water adjusted for us. And now he can adjust it from wherever he's at. He can take water out of the canal, he can put more water in the canal, release water out of Silverjack, whatever he has to do without making that long trip. And there, we eventually want to have everything connected together to where, it's on a time delivery system, because it takes 24 hours for the water to get through the system in there. So when we're on call, we're just like the Fire Mountain in there. Come after the 1st of July, basically we're on 100% storage water in there. The inflows are just about minimal. And the security of the ditch in there, the Cimarron area is prone to real heavy downstorms, to real heavy downpours in the summertime. We've had them come down like Coal Creek, for instance. If Raquel had the picture, I could show you what you don't want to have happen to your canal in there. And by this way, we've installed a bunch of wasteways that we're in the process of putting actuators and level sensors on. So if the canal gets a big influx of water, it can actually open the wasteway and let the water get away from the canal. Our system is set up, we've got 7 inflows into the canal. So them are just a few of the high points, so I won't pick up everybody's time.
And the other thing I was just going to quickly mention, I know when we went up to Silverjack, you had mentioned that, you know, with the installation of internet now, sometimes the ditch riders would go all the way up and then something was wrong and they couldn't communicate with anyone. So they had to drive all the way down to get some emergency fix. And now at least they can contact someone.
Yeah, they can contact for repairs like Brian Mitchum does a lot of our work. Brian might be somewhere in the world, as everybody knows Brian. But Trey can go ahead and he can get a hold of Brian, do a video chat with him and just show him exactly what the problem is. You know, is a wire connected wrong or whatever? Why he's standing right there, he doesn't have that drive time to get to communications, and that's very important in remote locations.
Great. One of the Steves, do you want to go next and talk about the benefits and why you installed it?
Well, just like Alan said, the efficiency is, you know, the main reason. And we're remote up at the County Reservoir also, and having the Wi-Fi up there has been very beneficial to where we can, you know, call out or have a problem, and even the water commissioners have got the password where they can, you know, stop in and make a call if they need to, because it's before you'd have to go clear down to Paonia to get any kind of reception at all, to do any calling on things. And as far as with the rest of the canal, there again, just efficiency on it, because we rely so much on our stored water. It's very important that we maintain as much of it as we possibly can for as long as we possibly can. This past year, we were out of water in mid-August and we were done. That's the canal went off and we were finished for the rest of the year. So it's very important that we can maintain, you know, as much stored water as we possibly can for as long as we can to make our water season, you know, last on out to the end of the year or the end of the water season.
And from our perspective, we have 5 major canals, and they divert a lot of water. So if you make a mistake taking too much, you have the ability to either leave way too much water in the creek or take way too much water out of the creek. And it just allows us to communicate from top to bottom with the different rides and there's a lot of people that, you know, that are reliant on everybody else's actions. And that's the main thing right there, is by having one central repository for this data and everybody having the ability to look at it, you improve your lines of communication, you improve your efficiency in your operations, and everybody knows when the water is going to come, what to expect, and there aren't any surprises, especially when you're dealing, like I said, with several hundred CFS potentially. So that's one of the benefits, I think. You know, some of the challenges are yet to be seen. You know, I think maintenance issues on it, I can see mossing becoming a significant problem in places. You know, things like that. But you know, constantly having to adjust the system, calibrate it, either have it re-rated with the impacts of mossing or different changes in our operations are going to be one of the things that we're going to have to deal with.
Yeah. Great. Tony, would you like to also add on the benefits?
Yeah, I think I covered it in the last slide, but the fact of the matter is we do have one ditch rider. covering a fair amount of ditch, and it was important for us to get the most utility out of that ditch rider, and spending time checking partial flumes or pond levels or adjusting meters is all part of the job. But what we wanted to do is make sure that when that individual was adjusting meters, getting out there, that we were getting our water to our shareholders as quickly as possible, that we weren't overfilling the pond and spilling it and pushing it down, some wastewater tributary to head elsewhere. We wanted to make sure we got that, captured that water and made it available to our shareholders. So again, it was just a matter of efficiencies, getting the most that we could out of what little we had.
Great. And Steve Pope, you started alluding to this, but I think it would be interesting for everyone to hear what the installation and operation and maintenance challenges are. And if you're having an outside party who's maintaining or helping you maintain your system, and how long did it take to learn? And I don't know, Tony, I know I've been leaving you as the last, but maybe you wanted to start first with that question.
Okay, I took my face off the big screen, so it was the main. Again, we're compared to the other companies here and the other groups, we're very new. We're the new kid on the block. We've been doing this, as I said, 8 to 9 months. I will say our startup has been, gone very well. We did have a few hiccups that you'd expect on any project. We're still working out a few issues and bugs, but again, very simple, very easy to start with. Our system is basic. We did not get into anything elaborate. We wanted to keep it simple. And if we decided to grow from that point, we would. And so again, it was a basic system, not a lot of frills, but everything that we did, we built with the idea of it being modular, or the idea that we could grow it to suit our needs. And as far as the maintenance go, and that was another thing that we were very cautious of, the last thing we want to do is inherit a lot of sunk cost or year-on-year cost that, as we're saving with one hand with the ditch rider, we're spending buying new meters, cleaning the system because of unforeseen problems. So again, we kept it as simple as possible. We went with the ultrasonic level sensors, basically systems that were tried and true. And from there, we can grow it and become more elaborate. But again, we always have to be cautious. So a combination of efficiencies and getting the most utility out of the water that we have, capturing it before it runs off whenever possible.
I think we're pretty new to some of it too. And a little bit of it, one of the scarier parts is trust. If you're sitting there at a computer and you said, okay, just pop the head gate up and I'm sending 500 CFS down this canal. I still send somebody out there initially, to be honest with you, and that's part of it, is you got to have faith in your system, have faith that it's calibrated correctly. And we'll work through that. And eventually, as being more practiced in it, you become more comfortable managing your system. That's when you really start to recognize the true benefit of being able to make these adjustments in a seamless manner, and everything is working smoothly.
Yeah, that is, and I think the cameras, for example, that Bostwick Park installed, I think maybe helps with that, with the trust of the system. But Steve,
Well, I was going to say trust. Steve talking about trust on the canal. I make the releases out of the reservoir, and you wonder, and we do have some redundancy, there's the gauge right below the reservoir, and a state gauge, and then on down the North Fork, you get into a USGS gauge, so you can kind of track, and see what's happening. But there's a lot of times I've made a release at 10 o'clock at night, and you wonder, man, I wonder what I did, and you want to jump the pickup and run up there, and kind of see what it did, and it takes some getting used to. There's no doubt about that.
Is Fire Mountain Canal maintaining the system, or do you have a third party who's doing it for you?
Kind of both. We maintain a lot of it, and then we deal with Mountain Peaks too, Brian Mitchum. And he does, the technical parts of it, I mean, we're new in it too, a lot of it. The system was up at the reservoir, and that's it was before I came in, but things have drastically changed up there to where we're new on it, and that's only been there for a couple of years, so. And on the canal, a lot of it's, battery powered, how long are these batteries gonna last, maintenance costs, that's yet to come. We have electricity at the reservoir and also at the main gate on the river itself. But the rest of it, we pretty much rely on battery pack, and solar panels. And so, I don't know, what the longevity is gonna be on that, it's expensive to put in at first. Because marine batteries don't come cheap, and like our trash cleaner, we got, there's 10 of them out there that operate that, so there's a lot yet, the unknown on a lot of that for us right now.
Well, I think not only is it working within your system, but outside, and we're very new to it, but I know that I've talked to other people that use it extensively on the Front Range, and from an administrative standpoint, they can track a rainstorm, and so they know by tracking that water through, they can just they can take so much CFS right off the top and administer it through their system as it's happening in real time, which is really impressive, to be honest with you. I mean, it's amazing how you can receive benefit over a 4-hour rainstorm.
And Alan, how about Bostwick Park? What are your main?
For most of the canal equipment, Brian Mitchum does most of that for us. For the main backbone, the internet, I actually hired the guy to put the system in part-time. So our system is up regardless, because he tracks it 24 hours a day. So, and we do have a redundant system. If our main signal goes down, it'll automatically route to a redundant system. So the system is never down completely.
Great. And was it?
Michelle, sorry to interrupt. I wanted to throw this in. The Clipper Ditch went ahead as part of the agreement with the company, the Intermountain Environmental. We went ahead and picked up a 2-year maintenance agreement with them up front. That's on labor. We do pick up the materials, but we did have build that into it. Plus, we had web hosting for a couple of years built into it also. That with the idea that this would get us up and running, and it would give us time to make a decision whether we wanted it long-term or to cancel or, come up with something different.
Great. Yeah, that is interesting. And I was going to ask you, Alan, and anyone feel free to add to this. Was it fast to learn the system, or did it take multiple months? Like, how was that process?
For us, because both my field civil superintendent and myself are fairly computer savvy. We've been around computers, we know how they work. So the learning curve for me was fairly fast. And Trey operated the Paonia Reservoir before Steve started working there. So he was already accustomed to remote control gates in there. So for us, it wasn't a real big learning curve in there. And with the high-speed broadband and the amount of broadband that we have up there, it is so fast. Our signal goes from the origination point there at the server at the office in there up to Silverjack in 2 milliseconds. We tried satellite communication, and it was always timing itself out.
Interesting. Has anyone else had a different experience where the learning curve was, a lot longer or more painful?
It's fairly quick. I can say it's kind of ongoing. I know there's a lot more to it that we don't know yet. We're learning every year. Oh man, I didn't know I could do that.
Maximizing the benefit of it.
And you definitely, there's a lot more benefits than what we're actually using. And we kind of put our system in to where we can add on, because we, looking at the master plan, like I said earlier, we want to put a regulated reservoir in, and everything's kind of set up now to where it'll all kind of tie in together, so it's a continuing learning curve, but just the basics, it's pretty simple.
Great. And so the last question for us to wrap up, and then we'll open to Q&A, is cost consideration. So how expensive the system was and how did you make it possible? Like what funds did you have to leverage to to be able to do things?
Well, and I think looking at the paperwork for our project, having not been involved with it, one of the benefits we have is we've got a fairly significant resources at our disposal for construction. And so we were able to handle all that. It was just more dealing with, Brian mentioned it, all of that kind of stuff, the technical part of it. So that was probably the easiest part for us. And then the cost consideration was the grant, because we did put in, there were several of them. It was not super expensive, but it was not cheap either. And that's why we thank the River District for some of that.
And thank the NRCS, I guess.
Yeah, NRCS as well.
Did all of you got RCBP funds, right? And I think it covered only like a significant piece of the project, but not 100%. So there was that, I guess with the benefits, maybe it was easier to convince yourselves or convince the board that that was the right way to go. But I don't know if that was a difficult piece of the project too.
For Bostwick Park, it wasn't a difficult decision for the board, for the simple fact that we weren't getting the job done that we needed to do because we're so remote and cover such a big area in there. The RCPP definitely helped. The rest of it was our construction funds in there. Trout Unlimited has helped us put in a lot of equipment. And when we apply for a grant, we include that in there. So most of it, I would say, most of it was done by grants, probably 50-50 grants and, the district.
Great.
As far as the majority of it was done by grants, we were RCPP, Water Smart grants to the Bureau of Reclamation, the CWCB, we got some grants to them, and they have used some River District and Conservation District funds also, on some of it, the planning and engineering and stuff. So I would say probably at least 90% of it that we put in was probably funded by grants, that we did.
Great.
I can address ours real quickly. Ours was all grants, basically. It was part of we built it around the fluctuation pond that we were putting in, because that was a critical component for the lower portion of our ditch for maintaining, uniform flow. And it was, again, the funding was through RCCP or NRCS, and it was, it was very helpful. Our system basically, as I said, was a simple system. So each data point, each data collection point, they were running between $5,000 and $7,000 for that data collection point, just to put some numbers to it. Again, based on the simple system that we had.
Great. All right. Well, does anyone have questions to our panelists? Go ahead.
Yeah, we're just getting our Salinity project started. When stockholders come back, they like all this stuff. We're going to get your money to put in, but who's going to pay for it afterwards? And it all has to be replaced. If you guys look at that, or are you going to try to raise assessments on your ditches to cover this stuff? Meters and stuff will go bad. You can get grant money to put it in, but later on, I suppose it's going to come back to us to have to maintain it.
Yeah, a lot of that depends by refocusing your O&M money in there, because the automation will reduce the O&M costs by a considerable amount. That'll take care of most of the equipment what it costs to maintain the equipment. You know, like us, we're kind of unique because we've got our own backbone system. It's a private system. And there, those costs are relatively not very expensive. They're expensive when they happen, but they don't happen very long or very often, except when lightning hits a tower. You know, when lightning hits a tower, it can take out, you know, $10,000 worth of radios and pretty fast in there. So you carry insurance on that type of stuff for lightning strikes. Basically, our insurance carrier, what they said is you just have to have a good grounding system in there to, you know, to protect, do as much physical protection as you can in there. That's a good way to cover the expensive costs. But you'll find that your O&M costs by automating this, you know, just like when Trey was having to go up to the head gate, drive 30 miles to get to the head gate, that's 3 hours time. You know, you got all those vehicle costs and everything, whereas now he can adjust the head gates and doesn't have to go anywhere. So that's a real money savings there because you aren't wearing out that vehicle, you aren't paying for the fuel, the fewer people can do more work.
Thank you. Next question.
Yeah, you talking about all this coming from grants, who's writing your grants? Do you have volunteers on your board? Are you paying grant writers? So how are these grants getting?
The district hires grant writers. Our engineer group, which is JUB Engineers, they've got a super good grant department. And they have wrote, let's see, Carrie, I think you wrote what, 3 grants for us?
Yeah.
Carrie with Trout Unlimited has written grants for us. So I would say by and large, the district hires its grant writers.
I'd say for the Clipper ditch, ours was a combination of in-house and grant writers, but again, I would strongly recommend getting a grant writer. They know the right wording. It's definitely going to save you time. They know how to approach the government and get it done more efficiently. For us, it's a series of mistakes and learning curves to decide what needed to be said, what should be said, and how to say it. So again, I think grant writers are, and we are using those now too.
Kel, we've got a note on that. Just in thinking about that, thinking outside of the district, like Alan discussed a little bit, sending water down the Cimarron. In 2018, I worked with the district to help shepherd water out of Silverjack Reservoir past their head gate. They take 90% of the water out of the river. So to keep a little bit of water in the river, I was up there all the time measuring flows, working with my brother who's their district manager to release water. I wrote a grant to CWCB, which helped pay for more controls and a new gate that we automated, and now it does our work for us. And it's really amazing. And I can attest to the power of the Wi-Fi at the head gate. I've taken a number of Zoom calls up there because I need to be working up there, maybe fishing or elk hunting or something, but it's really powerful. It's probably better than my house. So, but that work wouldn't have been able to be done without that automation and without TU writing a grant to CWCB and our money going into it, because we knew that it would essentially save the river, which it did.
Great. Thank you very much for that addition, Gary. The Uncompahgre or Fire Mountain Canal, do you guys also hire grant writers or you do it yourselves?
Previous grants, I think Steve might have taken a stab at a few of them.
Yeah, I was with Uncompahgre in my prior life, and with Fire Mountain both. I'm going to say there's a combination of both in-house and grant writing, you know, and there is a definitely advantage to grant writers, you know, I was real good at giving them all the information and putting it in. I mean, we'd spend hours, you know, even, you know, late at night, you know, through text messaging and everything, putting things together. But and and I've done a couple myself, in-house, but and there's a lot to it, to writing a grant. And I'm with Tony. I recommend a grant writer to help.
Quite
process
often,
go
yeah,
along.
quite often, I think some of our projects right now, we have an engineering consultant that's facilitating design of some things, and they have connections with, we start with the grant writing process there too, because they can provide that technical information that's needed to satisfy the grant requirements.
I think the grant writer should know water though. I don't think it's a good idea to hire a grant writer who just write grants. They need to know water.
I'll agree with that.
And I, yeah,
Oh, yeah.
you know, we
Completely agree.
we don't hire an engineer that doesn't know water. I mean, that's the problem. I mean, that's our thing is.
And we, with Applegate, we wrote a couple grants, Applegate that is, who did our engineering for us and have actually, worked on the getting the grants out, so.
Great. We have time for one more question, but we will have lunch and the panelists will be around and you can also, but go ahead, Carrie.
I'd like to know what the next steps are. I know Steve Fletcher was with us on the tour from the Palo Verde Irrigation District where we saw a pretty robust SCADA system, but the way they use it is to deliver or to use it to drive deliveries. So it's connected to on-farm use. It's the irrigator says, this is what I'm growing, this is how many days I need water. That gets transferred to the ditch company. And in this case, in Palo Verde, they're relaying that all the way to the Bureau of Reclamation, which is driving releases from Parker Dam, all in an effort to save water. And I think at some point, crop water use, consumptive use, evapotranspiration rates, cropping types, those types of things should be connected to our SCADA systems because we're not just delivering water to, deliver water, we're trying to grow food. And it seems like that should be the next step. Is that something that the ditch companies are considering?
Well, I think anytime we write a grant, we try to go out to as many of our users too, and they apply for additional funding for on-farm improvements in their systems. I mean, it kind of goes, I think in some ways it'll go hand in hand. Hopefully, as we improve our efficiency in delivery, they improve their efficiency in application. So and we can utilize that system to benefit both sides.
And Gary, I think it also depends on like the system that the on-farm users are having. If they're doing flood irrigation, maybe it's like they need more of a set amount of water independent of what they're growing. But I think with changes in the system and sometimes with the piping, what you're seeing is that the pressure from the pipe kind of incentivize producers to move into a sprinkler system or something. And I think then that could help too.
And it's kind of a canned question because I know the answer is Cimarron. Part of the grant that I wrote is we did the modeling to help determine how to best use the water resources. So you have a supply driven by the gauge on the Cimarron, and the demand is system loss plus irrigation demands, which is driven by evapotranspiration. So if cropping types change or efficiencies change, that can alter the amount of water that should be delivered out of the reservoir or diverted from the river. And so you can change these variables and it will affect the diversion rate from the river, which I think is, or the releases from the reservoir, which is critical. And reduce spillage.
Go ahead, Tony.
Real quick, I'll make this quick. One of the things is, we've been putting piping. That's been what started this whole process for us on the Clipper Ditch, pressurized on farm. You'll start seeing more and more center pivots and means of controlling, of distributing the water, less flood irrigation. But it also comes with its own set of headaches for us is that, of course, with a center pivot, you've got an on-off switch. Once you switch that off, you got to find someplace else to go with that water or you'll start spilling it. And so, that's part of the reason for the fluctuation ponds is making sure that we can control or manage and keep that water rather than having it hit a spillway and go, down some tributary, some dry wash and never to be seen again. And to Steve's question about how do you sell this to the ditch, to the shareholders, that's one thing that's always overlooked is that, the cost of meters, you've also got that's being offset by more efficient use of your ditch rider and less travel time. But there's also those opportunities to capture water and use it more efficiently. And we're hoping that we'll be able to find ourselves in that position, manage diurnal flows, catch those, we had it mentioned earlier, those storms, up country that are going to push water down to you, maybe get that on the fields rather than letting it bypass.
Great. Well, thank you, the four of you, very much for this conversation. And I'm sure you'll be around if people want to connect with them at the end. So thank you. And we can move, I guess you can leave the chairs there if they're extra chairs, but the last thing we have on our agenda is a couple of quick funding talks. And we have Brady McElroy with us from the NRCS. He is remotely. And so I will turn it over to you, Brady, and you can share your screen too.
Okay, thank you. Good morning. I appreciate the opportunity to be here, and I particularly appreciate the opportunity to do this remotely because my duty station is in Lamar. So there are some places in Colorado farther away from me, but not probably too many. I'm trying to share my screen. Is that coming through okay?
Not yet. There.
Okay. So I am Brady McElroy with NRCS. I am the state water management engineer. I work on our state conservation engineer staff out of our office in Denver, although I, like I said, live and work out of Lamar, Colorado. I'm going to give you just a really brief overview of our financial assistance programs, as I think they may apply to projects of interest to the group. And you've already mentioned several of the acronyms that I'm also going to throw around. And again, I appreciate the chance to speak to you today, and I've enjoyed learning from what the other speakers have shared. Give you a little history lesson to start with. I expect everybody's familiar with NRCS, but we had our beginnings back in the 30s because of the Dust Bowl. And in 1935, Congress passed the Soil Conservation Act, which began our agency. And actually one of the huge dust storms had reached Washington, D.C. while Congress was debating this, and that probably helped them garner the votes to pass it. So some photos there for curiosity's sake. The top two are actually taken in Prowers County, where I live and work. Prior to 94, we were really only a technical agency, but in 94, Congress reorganized USDA. We were renamed to the Natural Resources Conservation Service. And prior to that, we were largely a technical agency. We provided technical assistance to landowners, had just a little bit of financial assistance we could provide. Back then, FSA or ASCS at the time were really the money side of the business. In 94, we became increasingly responsible for not only the technical work, but also administering some of the financial programs as well. The mission of our agency is to deliver conservation solutions so that agricultural producers can protect their natural resources and the nation's natural resources and feed a growing world. And we do this by providing sound and science-based technical assistance, as well as financial assistance to producers to help them meet their conservation goals. There's a few of our programs listed on the slide. There are more that aren't listed. And I'm going to start talking a little bit about EQIP because I depending on the scope and scale of projects, EQIP may be an avenue for some funding, and then some of the other programs we offer kind of work under the EQIP umbrella. If nothing else, it'll give you a feel for some of the process. So EQIP is probably our biggest program that we offer to help with addressing resource concerns. And we have a suite of about 150 conservation practices that we can help landowners use to address their resource concerns. We help plan how to implement those, and then we can help incentivize the implementation of those practices. I would like to point out that EQIP and all of our programs are competitive. Not every project or application is necessarily going to be funded. The prioritization and ranking process to figure out which projects we're able to fund. And that's because typically we have a lot more interest than we have funding to go around. EQIP is pretty significant in scope. Colorado NRCS last year funded around 550 contracts for about $42 million. And we had considerably more applications than we had funding available. And if you extrapolate that out nationwide, there's significant investment in conservation across the nation. So, and I probably should mention that we offer incentive payments as financial assistance that can help cover part of the cost of implementing conservation practices. It may not, probably isn't intended to cover every cost, but rather to incentivize it to bring it into the realm of potential for clients to pursue those kinds of solutions. Bit of a slide here to show you the steps from application to implementation, and would like to emphasize step number one there, which is planning, and that's really a collaborative process between our agency and the landowners to develop an inventory and then a plan of how to address the resource concerns. And applying for funding comes a little later in the process. EQIP fund or contracts can be up to, I think, 10 years in length. Majority of them are probably in the 1 to 3 year range. And I believe one of the panelists earlier mentioned this, but you cannot implement any practices that we're assisting with until the contract is funded and we have an approved design in place for those practices. There can be a bit of a lag in the process. We accept applications continuously for standard EQIP anyway, but they're typically only processed in a batch once every year. Lately, the deadline seems to have been application cutoffs end in December, and the final obligation has happened around June. And that seems like a long time, and there's a pretty big workload. Like I said, we had 550 that we funded last year, much less that we processed. And behind the scenes, there's things like eligibility determinations going on. We're assessing and ranking those applications. And then there's a significant quality assurance process that's going on. The contracting regulations and policies are pretty onerous. I'm not going to spend a lot of time talking about these next couple of slides, other than to say that both the participant and the land itself has to be eligible for the program. So here's a few notes on the applicant and then some notes on the land. And both of those things, applicant and land, some of that depends on FSA records. So that's something to bear in mind if you're considering this, is to make sure your FSA records are up to date. And I talk about EQIP some because since 2018, we've been authorized to work with things called water management entities. Historically, we've typically worked with individual landowners or joint operations or some other business entities that farmers or ranchers have used to organize their businesses. But since 2018, we've been authorized to work with these other groups. Water management entities are things like irrigation districts, groundwater management districts, acequias, and other kinds of groups that have jurisdiction or responsibilities related to water delivery or management to eligible land. So this opens up the opportunity for us to work with some folks that we not necessarily have been able to in the past. And it's potential, there's some potential that ditch companies and groups like that may be able to work directly through EQIP now. But there's still eligibility requirements. The water management entity must be eligible, and the land must still be eligible. And there's a flow chart showing some of the eligibility determination process for water management entities.
Brady?
Pardon?
Sorry, we are just running out of time, so I'll just ask you to wrap up in like a minute if you can.
I can do that. I'm down to about 2 slides.
Perfect. Okay.
So I just want to say that determination of water management entity eligibility may be complicated. So work through your local field offices for that. These 2 things have been mentioned before. The RCPP program, that's probably more of a district or group kind of project rather than individuals, where you can use that to leverage some of our money with some of your resources. That may be for your grant writers, to where you apply through grants.gov for that. And I think one that may be of interest, and this was mentioned also, is the Water Smart funds. It's a BOR program, but at our national level, NRCS leverages BOR funds, so we can kind of combine some EQIP funding with BOR to work on some of these kind of projects. There's about a 1-year lead time. Our state office has to apply to Washington, DC for those monies. So if you're interested in that, please talk to your local field office. They'll get in touch with our program staff and work through that process. Last one is if you're not familiar with your local office, they're the first line of contact. Best way to find them if you don't know them already is just Google Colorado NRCS. When I do that, the second link is our contact page, and Western Colorado is in area 1, so you can click on that lower left-hand link there and figure out who you need to be working with. That's a very quick and very cursory introduction to some of our programs. I appreciate the time, and if there are questions, I can try to answer them, or I'll pass them on to our programs experts who definitely can answer them. So, thank you.
Thank you, Brady. And we have time maybe for one question? No? All right, well, thank you, Brady, so much. if you can, I think you have to stop sharing your screen, and we'll pass the slides around too. If you can email it to me and people can contact you directly too.
I will do so.
All right, so to wrap up, I will talk, and I will not take more than 5 minutes. So like the food is right there and I know everyone's hungry. I just have a few, where to go? A few slides prepared to talk also about funding. There it is. How do I- okay. Let me share. And so really briefly, and I will start again thanking Amy Moyer, who is our Director of Strategic Partnerships. She's the one running the new funding program with the Colorado River District. It's a new program. It started last year. And it's a lot of work and she's doing an amazing job and she's at another conference, so she couldn't be here with us today. But she was earlier. I think she's not anymore because she probably had to drive, but the River District now has a little bit over $4 million annually for water projects. And water projects within the River District's area, so 15 counties. High impact projects is what we're looking for. And if the funds are not used in a year, they can carry over. So anyone within the counties can apply. You can be government, you can be a ditch company, you can be an individual person. We do want to see a project that has partnerships. That's like one of the things we look at. So a collaborative project, and we're trying to leverage funds. So don't expect to come to the River District and try to fund a project 100% with River District money. That's not the intent. The intent is to use our funds to match other needs. And we also expect the project proponent to bring some funds to the table. These are the 5 buckets that your project can fit in. The more buckets it fits into, the higher chance of you getting our funds. So we have productive agriculture, conservation and efficiency, healthy rivers, watershed health and water quality, and infrastructure. So this last year, which was the first year of the program, $4 million. Actually, some of this was approved in our January meeting. So I think in 2021, we were close to like 3.2 million. But as of now, we've distributed $4 million to 28 projects, leveraging over $40 million for West Slope water. And here are some images of some of the projects that we have helped. And I think, Bob, you're right here.
Quick question. The 40 million that you leveraged, is that 36 million of in-kind contribution?
So not necessarily in
Other
kind.
funding?
Yeah, other funding, so state, federal. Briefly, we do try to encourage people to have a pre-application meeting for us to understand your needs better. We have 2 paths for an application. So if you're requesting less than $50,000, that can be reviewed and approved by our general manager. And we don't have a deadline for applications. It's on a rolling basis. So if you're going that path, you can apply at any time. And probably takes let's say a month-ish for it to get approved or not. If you're requesting more than $50,000, that has to be approved by our board. And our board only meets 4 times a year, January, April, July, October, that. And we need that application approximately 6 months before the meeting so that we can work and 6 weeks. What did I say? 6 months. 6 weeks. 6 weeks, definitely 6 weeks before the meeting so that we can work with you and evaluate it before we bring it to our board. So if you need more information, our website has a lot more information. You can contact Amy directly. You can reach out to me. This email is on our website. And this is the last slide. I quickly wanted to let you know about a couple of bureau funding that just became available that is perfect for SCADA. So this is Water Smart funding. What for you guys who don't know Water Smart, it's a grant opportunity within the bureau, but it has several like subcategories. And so one of the funding opportunities just opened up last week. So great timing for this workshop. It's the small water efficiency projects. Applications are due April 28th. It covers 50%, it can cover 50% of your project. And SCADA fits right into that category, as well as lining and piping of ditches, which is something we talk so much about. And I know there's a need, a big need in this area. They will be doing a webinar a week from today, Wednesday, March 9th at 1 p.m. Where they'll talk more about what projects qualify for it, what entities qualify. There's $5 million available. They hope to fund at least 50 projects, probably maybe more. The max funding is $100,000 per project, and the project cannot be more than $225,000. So it can't be a huge project. I guess if you want to pipe something, for example, it has to be just a piece of, the potential project. But this is really great, and there is some time, April 28th, and this is part of infrastructure funding, bipartisan infrastructure law. And so this should reopen every year, but this is what is currently out there. And then quickly, there is another Water Smart grant that just opened up called the Drought Contingency Planning. And that is to create or update drought plans. And this could be really interesting if your entity doesn't have one and you think that could be a really good thing to have. You can apply, also covers 50% of the costs. Applications are a little bit earlier, but it gives up to $200,000. They already had a webinar on this, but it's recorded and you can go into the bureau and watch it. So that is it. Well, I hope you all enjoyed. Thank you very much for coming. A little bit, there is lunch, so please eat and, talk. So there we go.
Thank you, Raquel.
Thank you.
Yeah. I did.